sorry for the delay. So thank you very much for the introductions. Thank you for all the organizers. So we already mentioned, our HPC training program at SDSC. We mentioned, of course, the Student Supercomputing Club and the organizers, and of course, Intel. And, I'll get a little bit more about acknowledgements. So I'm going to give about half an hour presentation as an introduction to this workshop today. What I want to talk about is porting of Amber to SYCL and give you just a brief overview. And what Amber is. You'll learn much more about SYCL is during the presentations later, the workshop, the tutorials. And so here's just a brief overview. Just to give you a quick background about what I do, I have a research group here at SDSC where we are working basically on molecular simulations method and software development. And a lot of what I do has been related to developing code for GPUs, graphics processing units, and then using those codes for simulations from atmospheric chemistry to biomolecular systems and both quantum mechanical and classical molecular dynamics codes. And so one of the major codes is Amber, and that's what I'm going to talk about a little bit today. And just let me start with acknowledgements about the work that I'm showing today, because it's always good to point out people initially, I think. And so that's in particular Huachan Chen and Ram Ramanujan from Intel. So they have been actually doing a lot of the great heavy lifting of this porting work over the last year, even a little bit over a year. So a lot of what I'm talking about has been actually implemented by Huachan. And then Kitar Ganesh, who's been instrumental, in setting up all our meetings and has always a great help and also has been facilitating this oneAPI SYCL tutorial today. And then, of course, funding from Intel through the oneAPI Centers of Excellence program. That's, of course, critical to get some of our work done. So just to give you a brief introduction, what Amber is. So Amber is basically two things. It sometimes confuses people. It's a set of force field parameters, which means, those are the parameters that are used in approximations, numerical approximations to describe how molecules interact, how molecules are built up and interact. And, currently there's a recommended set of force fields. They've been developed over decades for proteins, DNA, RNA, lipids, carbohydrates. So all the basic building blocks that build, cells and tissues in living beings, plants and animals. And then there's parameters for general organic molecules as well. So that means in principle, you can simulate anything. So it cannot be on, goes beyond biomolecular simulations, and then some experimental force fields and parameters for other stuff that's basically floating around in cells. Amber is also the name of a molecular dynamics simulation package. And so this has been around for about 30 years. There's about 50 principal contributors to the current codes. So it's a lot of lines of code and different programming languages. It's independent of the accompanying force fields, so it can also run other force fields, not only the so-called Amber force fields. And it's actually distributed in two parts. There's Amber Tools, which is completely free, open source, mostly GPL. It's on a yearly release, and that has a lot of programs. There's about like 30 to 40 programs. I even don't know myself off the top of my head. So preparatory and analysis programs in there and molecular dynamics programs. And then what's basically called Amber is just a single code. Actually, that's the high performance ND program that's under an academic licensing. So it's also free for academics, and you get the source code if you want to have it. And the release is every even year. And so that's the code that I'm mostly talking about today, because that's the high performance implementation that also has a CUDA implementation. And so, Amber overall has, Fortran, C, C++, CUDA, Python, comprehensive regression test suite, documentation. The documentation has over 1,000 pages now. So it is a big software package. And so if you go to that website, so you get a lot of information. And it's got a very active user and developer mailing list. We have, of course, best practices implemented for software engineering with revision control, code is hosted on GitLab. If you want to contribute, you can do that. You can get an account on that GitLab server. And, we have automatic CI tests, and of course, to keep quality of the code up. Here's some statistics about use and Amber use base. So it is a widely used software package. It's used both in academic and industrial research. It's had a steadily growing user base. It's installed on all major compute centers. And, so if you look at the user base, so these are actually licenses where we know that people actually have installations. And those are site licenses often, so they're used by many research groups. And they're in the thousands, and these are the different versions of Amber. So you can see initially we had like just, versioning numbers that went just 10, 11, 12, and so on. And then we switched to years. So 14 is 2014 and so on. And Amber Tools itself has a lot of downloads, but, these downloads, of course, we don't know how many people are actively using the code, but it's downloaded quite a bit. And these are the individual downloads of each version, right? And the popularity in particular has been growing since about 2010 with the release of the CUDA code. So that's the major code that's mostly used for simulations nowadays. And, it comes with a wide availability of GPUs that have enabled science for a large user base. And you can see this with the citations. So we published papers in 2012, 2013 about the implementations. And, they gather around 250 citations per year. It's actually more per year because in the first few years, it took some time to pick up. So that means that, there's every year, there's at least 250 research publications that come out that have been using that software package and the GPU implementation in particular and knowledge network. Popularity of molecular dynamics in general has been growing. So this is statistics from this publication here. So Tamar Schlick has done this nice work. And so you see different types of methods that are being used. So quantum mechanics, molecular mechanics, is also being used more and more. So that's another thing that I'm developing very strongly, but I'm not going to talk about today. But just regular molecular dynamics has been really taking off, and much more than comparable other methods, like say, for instance, ab initio molecular dynamics or Monte Carlo simulations. And in particular, if you look at the software packages for biomolecular simulations, so Amber is among the most popular codes actually. So you see it's basically leading the pack in terms of citations that publications are citing different software packages over the years. Romex is another code that is very popular. So that's an open source code. It's developed by a great European crowd. So those are probably the most widely used software packages. And overall, biomolecular modeling has been, gaining a lot of interest over the years. And, there was a lot of hype in the early 80s. Went down after the 90s, where people realized, well, it's great, we have these supercomputers, but the simulation timescales and what we can do with those computers is interesting, but cannot yet really solve challenging scientific problems. So gives fundamental insights, but is not yet practical for many applications. That has been changing, right? And in particular, since the let's say mid 2000s. Molecular dynamics, in particular, has been used more and more also in research to develop drugs and similar things. So it's actually quite productive, and in combination also with a lot of different experimental methods. So typical applications that we have. So you see from the different manual versions we have, always on the cover we have some sort of like biomolecule and its applications that demonstrate new applications that have been enabled by Amber, and all the different types of biological molecules, which are building blocks of cells and tissue, are studied, and it helps us understand how life works at the nanoscale. It helps us understand biomolecular function and disease, and it's used widely in computational drug design. And molecular dynamics simulations in particular give us information about the structure and function of biomolecular systems. So, we can study things like protein folding, enzymatic reaction mechanisms. So for those, we actually have to use the QMMM, so mixed quantum classical methods. But with classical methods, we can look at stability of protein drug complexes, as part of the drug design pipeline, for instance, to improve drug leads. And, there are many, many more applications that people are doing with it. And now if we look a little bit and take a step back about, initially I talked about force fields. And the question is, how do people model molecular interactions? So in principle, molecules are made up of, nuclei. So you see here a small molecule. This is an amino acid, I think it's cysteine. So here's a sulfur atom. So you have atoms that are built of nuclei and electrons. There's an electron cloud swirling around it. So in principle, you have to use quantum mechanics to describe the electron distribution here, solving the Schrödinger equation, which you see here, or you could use density functional theory, which is an equivalent method, but that's very expensive. So what people have been doing over the years have been developing molecular mechanics force fields that use simple ball and stick representations, and basically where you have very trivial representation of the connectivity in the atoms, so bonds here. So you can see you use a harmonic potential simply to describe the bonds with some force constant, and then you have like angles that describe how three atoms that are connected to each other are arranged preferably, and then angle bending, torsion terms here. And then there are non-bonded interactions with so-called Lennard-Jones potentials. So these are basically London dispersion interactions and repulsive terms once the atoms get too close. And charge-charge interactions, right? So there's a so-called partial charge. Each atom is polarized in a molecule and carries some charge with it. And so while these methods are very accurate, they're very slow. The quantum mechanical method and the force fields are very fast, That's why they're used, and they can still be used for some predictive representations. So what people are nowadays also doing is adding some machine learning models to spice up things a little bit. But for most applications, force fields are still used, and they will be used in the future. Now, why molecular dynamics powered by GPUs? Let me show you a few things just very briefly and make the case for that. So we see here, this is just fancy visualization of a molecular dynamics simulation that I performed a bunch of years ago, where we have identified a water exit pathway in this enzyme here that is actually embedded in a membrane, right? And so when you run these simulations, you have about 100,000 atoms, on the order of 100,000 atoms to 1 million atoms. So those are the typical orders of magnitude that people are simulating. And the relevant timescales that we are interested in are depicted here. So bond vibrations on the order of a femtosecond. So that's 10 to the minus 15 seconds, right? So that's very, very fast. And because of these bond vibrations, that's the time scales we need to do. We need to take into account for the time steps in our molecular dynamics simulations. So when we're simulating these atoms moving, every individual step that we need to compute cannot be faster than about a femtosecond. But what we're interested in usually happens on the micro to millisecond timescales. And so what that means is basically we need millions of time steps, right? And we don't want to wait years for the simulations to finish. So that means that basically a single force computation, the energy and the force that's acting on the atoms during molecular dynamics simulations has to be done within about a millisecond or faster. Right? So we have hundreds of thousands, millions of atoms, and the interactions of that equation that I've shown you before need all to be computed within a millisecond, right? So that's a lot of compute in a very short time scale that we need to do. And if you implement it correctly on GPUs are very powerful, you can actually get very high performance. So here's a comparison of this, a few years old, but it looks very similar. So the V100 GPUs here on top are the ones that we have on SDSC expands. So that's NVIDIA hardware actually. And what you see is the time it takes well, no, that's basically how many nanoseconds. So that's basically this order of magnitude here. So 10 to the minus 9 seconds in the life of a molecule, in this case, a cellulose strand, so about 408,000 atoms solvated in water, you can simulate in a day. So this is a typical benchmark. And that was at the time some, basically top of the end CPU cores, CPU nodes with a high performance implementation of our molecular dynamics code in Amber. And you could get about, say, 2 to 3 nanoseconds per day, right? A single GPU implemented correctly gives you about 50 nanoseconds a day. So you can, on a single GPU, basically get 20 times, 25 times as much science done as on a single CPU node, and that's why people have been using more and more GPUs for molecular dynamics simulations. And when you program these things, you have to be careful on how you implement this, right? So you'll learn a little bit on how to use SYCL for targeting GPUs or hardware, multi-core and many-core hardware in general. But if you do something like you want to compute the force due to a pair potential Vij, so if you look at this, the forces are conservative, which means the force on atom I exerted by atom J is the negative of the force of atom J on I. So when you look at this in terms of a matrix Ij, where I and J are indices of atoms, you need to compute only half of the matrix, right? And what we do is we have hundreds of thousands of atoms, and we subdivide that basically into tiles that then execute the threads that are executing and computing your interactions, executed in the right way so that we avoid race conditions and optimize performance by dividing the calculation basically in such a way that read and write operations to memory can happen at the same time. A warp that's NVIDIA specific, but just think about it as a number of threads that are operating together in lockstep. We distribute basically these tiles of work to the different processors. So SMs are processors on GPUs, and if we do it correctly, we use offsets to avoid race conditions. And what I mean with that, for instance, we're computing these different diagonal and off-diagonal types. It's the same in both cases, only here we don't need the interaction, an atom doesn't interact with itself. While here, we have two different atoms interacting, and, you start basically different threads here symbolized by the blue dots at different offsets in your arrays. And this way, you can do a computation, you read the data from registers, do your computation and store it into shared memory. And each thread can do that at the same time without having to write to the same memory location. And so these are a little bit of some of those things that you have to keep in mind when you program for GPUs. Other things that are important, so one of the things that we've been doing to get high performance is use 32-bit floats instead of 64-bit floats. And when you do that, you have to be very careful because, a 32-bit float has approximately 7 significant figures. So when you add two small numbers, you're fine, right? So here on the left side, you just lose one of the significant figures of the smaller number here. That's okay. But what if you have already a large number because you've added a lot of interactions from many different atoms, right? And then you lose everything, right? That's a problem with molecular dynamics, and it happens in many of the different algorithms that we use under periodic boundary conditions, shape algorithms, force accumulations in particular. And so what you need to do in this case is you need to make sure that the accuracy is maintained, and there's a lot of information here, but let me just tell you about this here. SPFP, that means, we're doing all the individual computations single precision, and we do the accumulation of the data in 64-bit fixed precision as a hybrid. So instead of using double precision, fixed precision, the reason for doing that is because integer operations are faster and they're usually more integer compute units available on GPUs. And this is just to show you, right? I mean, this is the energy, average energy, or it's the energy over time minus the average energy of a simulation. And If you don't do anything, you have no thermostat, so you're not adding any noise to your simulation, no heat. The energy must be conserved, right? That's just basic Newtonian mechanics. And if you compute everything in single position, and we had an implementation for the CUDA code initially, it just blows up, right? So the simulation is not numerically stable. But then if you use fully double precision or this mixed precision, so SPDP was the predecessor to SPFP, everything is fully numerically stable, right? So you just need to know what you're doing and be careful about what you're doing. And that's just to show some additional numerical data. So you can see SPFP still has a large error. Let's just look at the maximum error of force computation compared to the reference implementation and the implementation on the GPU using double precision. So it is 4 orders of magnitude less accurate, but it is sufficiently accurate to conserve energy, as you've seen on the slide before, simply by being more accurate than doing everything in single precision. So these are some of the things that you need to take into account. So I talked a lot about Amber, but now the question is porting Amber to SYCL, and so I've shown you that the CUDA code is, well, I've not shown it to you, but it is one of the fastest, if not the fastest, classical molecular dynamics code for NVIDIA GPUs. It enables microsecond molecular dynamics simulations on single gaming GPUs. Even you can buy a cheap GPU and actually do some science on it. It also enables large-scale ensemble simulations on GPU clusters, so it's also used on the largest supercomputers that we have. So it's a very successful and popular code. And so why then do we want to port Amber to SYCL, right? And there are many reasons for that. And one of them is we want to enable Amber to run on Intel GPUs, right? SYCL is an open standard, CUDA is not. We also want performance portability, right? So we have code that runs on NVIDIA GPUs, but we want to run on Intel GPUs or also AMD GPUs. And currently, we have a code base that has already, CUDA, it has HIP and ROCm for AMD GPUs, but we want a single code base to keep the code maintainable. And so SYCL is basically what we hope will lead us down this way. And one of the reasons to use Intel GPUs, very obviously, you just look at, for instance, the Intel data center GPU Max. I think we'll probably hear a little bit more about those today. I don't know exactly what's contained in the follow-up presentations, but let me just very briefly mention that this is a very powerful, very interesting GPU, and it powers, for instance, the exascale supercomputer Aurora at the Argonne National Laboratory. So that's some very serious hardware. And just to go through it very quickly, architecture is quite interesting. It consists of so Intel PVC, it's often called PVC. Ponte Vecchio was the code name. Consists of up to 2 stacks, and then if you look into this, each XE stack contains up to 4 so-called XE slices that contain 64 XE cores, ray tracing units, and hardware contacts, and then also HBM2E controllers, so that it's connected to high bandwidth memory. And it also has XE-link high-speed coherent interconnects and cache memory. And then if you zoom further in, each XE slice contains 16 of these XE cores, has 8 megabytes cache, bunch of ray tracing units. And then if you look at an individual one of those XE cores, it contains a vector and matrix ALUs, and each vector engine itself is 512-bit wide, right? So basically allows 16 FP32 SIMD operations with fused FMAs. And the matrix engines are 4K kilobit wide, basically. And so it's very interesting. And then if you look at the specs, right, the peak throughput of that hardware, and FP62, 64 and 32 gives you 52 teraflops, right? I mean, so that's pretty impressive hardware, right? And if so we don't do this in Amber, but I mean, if you have machine learning workloads, there's these matrix extensions for 32 floats and bfloat 16 and FP16 and so on. So you get very, very large number of machine learning operations. So it's very good hardware. very interesting hardware, and that's really the reason why we really want to have our code running on that hardware. And what are the challenges? So it's this code that currently is, the CUDA version is called pmd.CUDA. So pmd is the particle mesh eval molecular dynamics code. It's just a complex code. It has many different methods with many different code paths. So-called implicit and explicit solvent molecular dynamics code paths under periodic boundary conditions. It has different thermostats and barostats. Many enhanced sampling and free energy algorithms with restraints for umbrella sampling and similar things, steered molecular dynamics, thermodynamic integration, and so on. And then there are other code paths that enable ensemble simulation methods, including temperature and Hamiltonian replica exchange, constant pH, et cetera. So there's many different methods implemented, and of course, that's amounts to a lot of different lines of code and functions that need to be ported. And of course, these are implemented in different, precision models. And then we have single and multiple GPUs, of course. On top of CUDA, there's also an MPI parallelization so that we can use the code across multiple GPUs and across multiple nodes. And what we started with is basically with a single GPU implementation, right? So that's a very common use case and the most widely used case. It covers the most widely used approaches, including particle mesh eval, thermostats, and barostats. And then at a later stage, we'll move toward advanced features, including everything that I mentioned on the slide before. And this is an analysis that Gurchan made, about the PMD source code statistics. So it's mixed Fortran 90 and C. Here's the CUDA source directory. If you look at that, in particular at the CUDA code, we have tens of thousands of lines of code. There is 459 global CUDA kernels and 282 CUDA device functions. So, you see there's a lot of code that needs to be ported. And how to do that, that's what you're going to learn today, at least get an introduction. And so just let me tell you very briefly, I don't need to tell much about it. You're going to learn more, but SYCL is basically single source, high level, standard C++ programming model that can target a range of different heterogeneous platforms. So different types of GPUs, multi-core CPUs, even FPGAs, right? And it's an open standard, multiple vendor support. And so there's all this vendor domain down here that you as a developer really don't have to worry about. And there's the developer domain. So there's different libraries from et cetera, and you can use different compilers, and there's a lot of software available. And so Intel oneAPI is a key player in that ecosystem. So you have your source code, and you can compile it with SYCL, there's compute-CPP, multiple backends, and there's Intel oneAPI. And so that's what we're going to look at closer today. So you learn something about that. And the way you start, and you can do this starting from CUDA to a working SYCL version. For instance, for Amber that we've been going is to migrate the CUDA code via the Intel DP C++ compatibility tool. Now there's an open source version, that's the recommended version. It's called SYCLomatic. So basically you run that over your existing code, if you have an existing code, right, like Amber, and then you compile it using Intel's oneAPI compilers. You fix compile time errors and warnings, and there's still many things to fix, but SYCLomatic is a pretty good tool that helps you get 80 to 90% of your code ported, and then you debug, verify for functional correctness, and profile and optimize on Intel GPUs, and that's where we are at right now. And if you look at the code that's generated by SYCL, in SYCL, looks a little bit longer here, it's maybe a little bit more descriptive, but you see here, for instance, you get some information also when with comments from SYCLomatic. The kernels are quite similar, but of course, they look different. It's C++, and but it's, if you have CUDA code, it's not too hard. It's doable to get basically SYCL code, even for a complex code. It's not trivial. It took us a year to get there, over a year, but we got it done. And we are at the place where we can now optimize. We know that the code is numerically correct. So here's a simulation example where I told you the energy needs to be constant, so there shouldn't be any energy drift. There is a small energy drift, but you see the order of magnitude of the total energy, and the drift is very small. This is to be expected due to numerical settings in the simulations. The important piece that you see here is that the SYCL code really reproduces the CUDA code. So we actually really have a functional implementation that works correctly. So kudos in particular to my collaborators at Intel for this great work. And with that, I don't want to bother you more. So you want to learn something, but let me just tell you. So we have about Amber. We have the high performance GPU molecular dynamics engine ported from CUDA to SYCL. A functionally correct version that supports particle mesh eval simulations with different thermostats and power stats in both the SPFP and the DPFP precision models. And so what we're going to do now is profile the source code and optimize performance for Intel GPUs. And then we'll move ahead to port missing features, including restraints, all these enhanced sampling algorithms that I've been talking about, and replica exchange methods that will then be enabled by multi-GPU via MPI. So that's what's going to happen over the next months and year. And I look forward to have a source code that is capable of running efficiently on Intel GPUs, but also portable and works on other hardware, including NVIDIA and AMD GPUs. And so that's a little bit of an introduction of what we've been doing. With that, thank you for your attention. If there are any questions, I'm happy to take them. Otherwise, I'll let you move ahead and actually learn how to use SYCL and, hopefully have a great experience with the rest of this workshop. Thank you.
All right, thank you. So let me share my screen. Hi, I'm Rakshith. I'm a developer evangelist at Intel. So today will be conducting a workshop mainly focused on SYCL programming. So let me pull up the agenda here. So hopefully you're able to see my screen.
Yes, you can see it. Great, thank you.
Yes.
Okay, so I'll turn off my video and continue with the presentation. Okay. Yeah, so I'm Rakshith. I'm a developer evangelist at Intel. So my focus currently is mostly on oneAPI and high performance computing. So I mainly conduct training on high performance computing, mostly focused on SYCL programming and tools. So any other training content or samples with SYCL, I can help you with that. And Ben?
Ben, quickly.
Oh, yeah, sure. Hey, I'm Ben Odom, teammate of Rakshith's here. I work, I kind of got 1 foot in SYCL and 1 foot in Python, Intel parallel Python AI efforts. Really looking more at machine learning type things like XGBoost. Very similar role though. We're here to help you guys learn SYCL. Hopefully you can take advantage of it, expose you to our hardware and how you can maximize your productivity, and show you how oneAPI can help you, develop a heterogeneous mindset and application, so you can get that best possible experience with the portable code.
Okay, so with that, I don't know where I got cut off, but I'll go over the agenda again. So mainly we'll start off with C++ code to SYCL. So assuming that you have only knowledge of basic C++, we will introduce you to some basics of SYCL. And then the next session is SYCL Essentials. Mainly we'll go over more programming basics of SYCL, how the memory models will work, and then a brief overview of kernel programming. Then later on, we will look into SYCLomatic Tool. So this is the tool that you can use to migrate your CUDA code to SYCL. brief introduction to that. And then finally, we'll end the session with some tools. We have the Intel VTune Profiler to profile your code. And then there's also the Intel Advisor tool. This will allow you to check which parts of your code will perform better if you offload it to GPU as an example, right? So that's in the agenda. So to start off with, let me go over why oneAPI came into existence, right? So in today's world, we have a bunch of different architectures, right? We have CPUs, GPUs, FPGAs, and there are other accelerators out there. So if you want to program currently for all this hardware, there's different types of programming languages, the different set of tools for each one of these architectures, right? So this is the problem, and then the main problem that oneAPI is trying to solve is trying to get a common set of programming tools and programming languages that will work on all these different architectures. So not only different architectures, but even these architectures from different vendors, so that you can have one set of tools and one set of programming language that works across all these different hardware, right? So that's mainly the goal. So the oneAPI industry initiative mainly tries to solve that. You can see on the right here, there's all these different hardware, and then oneAPI mainly tries to be the one solution which will work on all these different hardwares. So you'll have the main programming language, which is SYCL, which we'll mostly learn today. And there's also all these API-based programming like the parallel STL, there's the AI analytics library or video processing library. So those all work in this layer right here. Right, and the oneAPI toolkits are free to download. So you can, best way is just if you just Google oneAPI based toolkit, download, and then you'll be able to download this onto your either Windows or Linux machine. And it gives you a brief overview here what each one of these toolkits contains. So the base toolkit will have the basic programming languages, the compilers that you need. And then for each domain-specific toolkits, you will get the appropriate tools. For example, the AI toolkit will get you all the AI frameworks, and the HPC toolkit will get you the HPC-specific compilers like the Fortran compiler, OpenMP compiler, and the tools that are needed, right? So today's workshop, mainly we will be doing on the Intel Developer Cloud, and that already has all these toolkits installed and configured, so you can just log into Intel Dev Cloud and then get started with, right? So that's the introduction. So with that, the first topic today will be we'll learn about C++ SYCL, right? So mainly we will learn how to use SYCL to offload computations to an accelerator, right? So the main objective of this session is mainly to learn how to use SYCL to offload computation to accelerator. So this accelerator could be anything like a CPU, GPU, or any other FPGA or any other accelerator, right? So we will learn why we have to use SYCL for offloading computation. We will look at C++ SYCL example, and then we will learn how to compile a very basic SYCL program, right? So to understand that, we will try to understand why offload computation, right? So mainly the large computational problems run substantially faster when you run on specialized hardware like GPU than running on a CPU. That's mainly because GPU, as an example, can run many small computation at once by making use of parallelism, right? So that's why it's important. So instead of running your code just on the CPU, certain types of computation can actually be offloaded to GPU, and then that will run faster and give you better performance. So that's the main reason for offloading computation. And we do this by using SYCL. So why SYCL? So mainly because it's royalty-free and it's cross-platform abstraction layer that enables you to code for heterogeneous computing. It offloads processes to be, it offloads the computation so that and it can be written using modern C++. It mainly provides abstractions to find devices, because currently C++ does not have that capability. So that's why we use SYCL, which will give you APIs which will allow you to find the different hardware on the system, and then you can execute code on these hardware, whether it's CPU, GPU, or FPGAs, and then you can manage data and also do code execution on those devices, right? So that's what SYCL enables you to do. So to understand that, so let's look at why SYCL is a good choice for accelerating your code, mainly because it's an open standard. It supports multi-architecture, right? So it supports whether you're using CPU, GPU, FPGAs, or any other architecture. It gives you freedom from vendor lock-in. So what this means is that if you've written a code for GPU, so then that code will run regardless of which GPU you're using. So you could be using an Intel GPU, NVIDIA GPU, or AMD GPU, and SYCL will enable to work on all these different vendors, right? And also it's an extension of widely used C++ language, right? So that's everybody knows C++ coming out of college. So SYCL is just an extension, like a template library on top of SYCL. So it's easy to get started. So that's another advantage. And also migrating from different code bases to SYCL is also easier because there's a tool that's being developed called SYCLomatic, which is an open source tool which will currently allows you to migrate your CUDA code into SYCL code, and then you can run that code on different hardware rather than just running it on NVIDIA, right? So that's one of the advantages of using SYCL. So and then the oneAPI toolkit actually provides you a compiler. This compiler can be used to compile your C++ SYCL code, right? So this is a compiler which supports the open SYCL standards, and it also has some Intel specific extensions to get you better performances. So we will be using this compiler to compile the SYCL code. Right. So with that, so let's look at some code, right? So let's look at this simple C++ code, right? So all it's doing is, so I think most of you are familiar with this one, so you can easily read this code and see what it's doing. So what it's doing is, first we are initializing some data. So that's this section of code here. So all it's doing is it's got an array of 16 elements, and then each element in the array is actually initialized to some value. In this case, it's initialized to value of I. So that means that if there are 16 elements, the values are 0, 1, 2, 3, and so on until 15, right? So it's simple. We initialize an array, and we are doing some computation on that array that we just initialized. And as an example here, what we are doing is we are multiplying all the elements by 5, right? So this is our simple computation. So this computation can be anything, right? So you can actually have a really complex algorithm here. But to understand, we're just making the computation very simple. So let's say we have, our goal is just to multiply all the elements by 5. That's your computation here, second step. And finally, we just print the output, right? So this is our simple code. Right. So our next goal here is to do this computation on the GPU. So this section of code, what you see, let's say you want to run it on the GPU. You want to do this computation on the GPU, right? So how do we do this, right? So that is what SYCL will help you to do, right? Because with C++, the code that you run will execute on the CPU. And now if we want to offload a section of the code to the GPU, that's when SYCL comes into picture. So to understand that, so let's do a side-by-side comparison of a C++ code, and then how it would look if you introduce SYCL into it, right? And with that, so let's look at this code, right? So you can see that most of the code is still the same, right? But there is some extra code that's been added, which are SYCL specific. That's what enables you to run this code so that the section of the code will run on the GPU. So let's try to understand this, right? So let's see what SYCL is doing here. The first thing it's doing is it's selecting the GPU device for offloading. So that's this line of code here, right? So this wasn't in the original C++ code. So what we've done here is created what's called a SYCL queue. And you can see we are doing something called the GPU selector, right? So this code, what it will do is it's just selecting a GPU as your offload device. And the second thing we are doing is changing the way we are allocating memory so that both host and device can access it, right? So you can see that before this in the C++ code, we just had a float of data, right? So instead of that, now we have something called malloc shared. And if we allocate the memory this way using this malloc shared, this data can be accessed both on the host as well as on the GPU device, right? So that's another thing that's different. And the third thing is how we actually submit the computation to the GPU. So initially we just had this for loop. Now that entire for loop, basically the entire computation is wrapped into this call called the queue.SYCL task, and then we wait for the completion of this one. So this is the code that will mainly send this computation, basically this for loop to do multiplication by pi. It's offloaded to the GPU. So this is mainly what SYCL will do. So these three things will enable you to write SYCL code, and then this code will actually run on GPU. Or if you change this to something else, right? Instead of GPU, you can just change this to FPGA selector, for example, or any other accelerator. So then this code will be offloaded to that specific device, right? So this is mainly the basics of SYCL. So you can see that it's very simple. We've included one header file. So this is new. And then we've done three different things, right? Selecting a device, allocating memory, and then submitting the kernel itself. So this is basics of SYCL. So with that, so let's try to understand each one of these steps, right? The three steps that we just learned. So you can see that in this first step that we've done, we've used something called a SYCL queue, which is mainly used to schedule a task to execute on the device. And the device can actually be specified when the queue is constructed. So that's what we've done here. We've specified a queue, and this queue is actually used everywhere, right? This queue is used for memory allocation. This queue is used to submit a task. And then you can see that we have selected a device here, right? And there are various ways you can select a device. So in this case, we have specifically said GPU selector. You can also say CPU selector, and it will just run on the CPU. Or if you have any other accelerator, you can say accelerator. So that is, if it's not a CPU or a GPU, then you would just use accelerators. So this is like a catch-all kind of selector. And then finally, you have something called a default selector. So to understand that, so right now in your code, you specify it as a GPU selector, right? So if you try to run this code on a system with GPU, this will work fine. But if you try to run this code on a system that does not have a GPU, then you will get a runtime error, right? So you should really be using a GPU selector if you know for sure that your code is only being run on a GPU. But if you are planning to run this code on any device, then it's probably better to use this default selector. So if you use default selector, then it will first attempt to run on a GPU. And if it finds a GPU, it runs on the GPU. If it does not find a GPU, then it falls back and then runs on the CPU. So at least your code will be executed. It may not run as fast, but at least your code will execute without throwing any errors, right? So that's when you would use a default selector. And the last one is just the same as default selector. If you just don't specify, if you just create a queue as a like this, then it's same as using a default selector. If it finds a GPU, it will run on GPU, right? So we will be learning a lot more in detail about this device selection when we go into the SYCL Essentials module. But this is the basics, right, of device selection. So this is something you'll see on probably the first line of code in any SYCL program, right? Because you have to first select a device. Right, and the second step is memory allocation, right? So you can see that in the C++ code, we just had a float of data, right? And we've just changed that into a slightly different format. We are using this new function called malloc_shared. So the name kind of tells you what it's doing, right? It's mainly memory allocation, which is shared. Shared with what? Shared with the host as well as whatever is the queue, right? The queue is selecting a GPU, and that's how the compiler knows that this particular data allocation can be accessed either on the host or on the GPU device that it's selected, right? So so if you use something called malloc shared, so easily you can access that same data element on the host. You can see that on the host we are modifying it. And in the kernel code here, when you do the computation on GPU, you're accessing the same data, right? And all the in between here, right, before it jumps from this line of code to the code that runs on the GPU, the memory is actually migrated. It's transferred from the host memory to the GPU memory. So all that happens automatically under the hood. So all you have to focus on is just writing the code. Okay. So eventually you'll start learning that there is a different way to do this allocation. So this malloc_shared actually does allocation so that it can be accessed both on host and device, but there is a device specific allocation, right? In some cases, you might want to allocate memory only on the GPU, and you want it to retain on the GPU while doing computation. So for that, you might use something called malloc_device, and we will learn more about that in the upcoming module. So this is mainly more useful to get performance out of the box. And that also, if you use this malloc_device, you'll have to move the memory explicitly, which we will look at examples later, right? So this is about memory allocation that we've done. And finally, the third thing is submitting the computation to GPU, right? So currently we are doing that using what's called a single task. This is the most simplest way to do allocation, where you can just wrap your entire code that was running on CPU inside this single task, and this entire thing will execute on the device, right? Which is, in our case, it's the GPU. And at the end of it, you can see that we are using something called a wait method. So this is mainly because when you have computations on two different devices, the computation happens asynchronously, right? So you have to wait until the computation is complete, because the host is waiting until the computation on the GPU is complete, and only then you can print out the result, right? If you don't have this wait, then this print actually happens while the computation is still going on, and you may not get the right result. So that's the reason you have this wait, which will mainly help you to synchronize between the GPU and the CPU. And then this wait method will mainly help you to pause until the computation is complete, and then you're ready to print the output, right? So hopefully this helps you understand the entire code. And then there's also something called, we've used q.singleTask, right? So there's also something called q.parallel_for. That's a different way to submit your computation to GPU. This is mainly used when you want to enable parallel execution on the GPU, right? So we will look at that example in the next slide. But then again, we will be learning more about all of this in the next module in more detail. But this is just an introduction, right? So this is the code that we have right now. So I was talking about parallel execution. So if you want to take the same code and then do parallel execution, then you would mainly change the single task into parallel for, and then inside this you would specify the total number of elements and then each index. And you will notice that we've gotten rid of this for loop here, because this entire parallel for will act as a for loop, but then all the elements are executed in parallel. So that's the main difference between the two. The first one, single task, it's mainly just used to wrap the entire computation. But then if you notice that the code can be executed in parallel, especially if you see that there's a regular for loop inside for your computation, you can get rid of that for loop and then use parallel for. So this will give you, better performance. So this is mainly what your SYCL program will look like. Most of your code will have these three components, right? The device selection, the memory allocation, and then submitting the kernel, right? So if you know these three things, this will mainly enable you to write a SYCL program and start offloading your code to GPU. So this is all you would need to know to accomplish that. So the rest 80% of SYCL is mainly how to optimize your code for the device it's running on, right? So all the optimization is the rest of the 80% of SYCL. But if you know these three things, then you're ready to get started, right? So once you have the code, so how do you compile, right? So for that, there is a compiler available that comes with the oneAPI based toolkit. It's the Intel oneAPI C++, DP++ compiler. It's available inside this oneAPI based toolkit, and the link to installation is in this presentation. So I will be giving this presentation at the end of this workshop, so you will have the link. So it's free. You can install it on your Linux system or on your Windows machine as well. And how do we compile your code? You first set the environment variable, and then if you're just compiling C++, you would just use ICPX as the compiler name, and then specify the source code, the C++ file. But then if you're using a SYCL code and you're compiling SYCL for Intel CPUs and GPUs, then you would use this FSYCL flag, and then this is how you would compile, right? And then what about compiling the SYCL code for, let's say, NVIDIA or AMD GPU, right? So for that, again, it's the same thing. You need to install the oneAPI based toolkit, right? And then there's also this plugin from CodePlay for oneAPI compiler, right? So this is something you need to install. This plugin will mainly enable you to compile for NVIDIA and AMD as well. And then the method used to compile is the same. We set the environment variable. If you want to compile for Intel CPUs and GPUs, it's straightforward. Just use the ICPX and then FSYCL flag, and then specify the source file name. If you're compiling for NVIDIA GPUs, you'll use the CLang compiler, and then you would specify the NVIDIA target and then the same file name, right? And same thing for AMD, you specify the FSYCL target, and then that's how you can get the same code to actually compile and run on different hardware from different vendors. So with that, so let's look at this code, right? The code that we have, C++ and SYCL code. So we will try to run that together on the Intel Dev Cloud. So let me pull up the Dev Cloud, my browser window, right? So hopefully people have registered for the Intel Dev Cloud account. So if not, I will paste the link here. So if you go to this link that I pasted in the chat window, you will be able to register for an account. And once you've registered, if you've signed in, it should show on the top right corner that you're signed in under your user ID. So once you're here, if you go to Get Started, and if you scroll all the way to the bottom, there's an option called connect with Jupyter Lab. So let's click on this option here, Launch Jupyter Lab. Okay. So if you click on this Launch Jupyter Lab, it should actually launch you a window, something similar to this here. You can see that the Jupyter Lab session is running here. On the left-hand side, you will see a bunch of folders which are different training modules. On the right, you'll have the main control panel, and we will look at how to use this one. So I'll give some time. So let me know if people want to follow the live workshop and then execute code. You can log into your dev cloud and then arrive at this Jupyter interface. In the meantime, I'll see if there's any questions to answer.
Hey, Rakshith, one of the people asked why are we using Q single task, and is it just for serial execution? And I kind of amended it, saying it's actually so you pick a single work group for a particular work item. But
yeah, so it's mainly, I mean, we used single task is like the most simplest way to offload. So that's one of the reasons I started off with single task, because and then led into, right? So if you use single task, it's mainly, it is serially executing. It's running on a GPU, but it's serially executing. So that's why we plan to use parallel for eventually, right? But single task is the easiest way for you to offload any computation, right? So before this code, if you go back to the
and it allows you to index it, right? Super easy, like off the 0th or something crazy like that. Like
I mean, because you don't have to worry about like any of the indexing. So if you look at the code here, right, C++ to SYCL transition. So if you use single task, you don't have to change any C++ code, right? Your entire computation in your C code will remain the same. You're just wrapping it with this single task, right? But then our goal here was just to offload the computation to GPU. But if you want to get performance, the next step is to change the single task to parallel for, and then you can actually get rid of this entire for loop, and then you're actually running in parallel. So all the items will get executed at the same time instead of having get execute serially on the GPU. So that's the main reason.
Nice. And earlier, Yogesh asked a question, and I'm not sure you actually did answer his question, but he wanted you to explain a little more about data and memory. Is data exclusively in main memory or GPU memory? And maybe you could explain the relationship between, the problem you're working on and how that memory is shared or moved around between the system memory and the device memory.
Yeah, so mainly if you look at the same code here, right, on the C++ side, it's pretty obvious that this, when you say float data, so this memory is on the system memory, right? But when you're starting to execute code on the GPU, so that's why we are changing that to use malloc_shared. So this will allow you to have your memory either on the host or on the device, right? So in this case, you can see that we've done a malloc_shared allocation. So at first, we are mainly initializing this data on the CPU, right? So this allocation, this data will remain on the system memory. And then when you go and try to offload this task, the compiler will notice that this data is actually executing on the GPU now, right? So then the compiler will automatically migrate this data from system memory to GPU memory, right? Only then this piece of code will start executing. So you will see like when you execute, there are two things that are happening since this is accessing data that's actually on the host. First thing, this data gets copied over to the GPU, and then the computation is done. And then when it comes to printing out the result on the host, again, it notices that the data is now on the GPU, right? So an actual transfer happens here, and then the result is being printed out. So all that transfer of data from system memory to GPU memory happens automatically. The compiler takes care of it when we are using something called malloc_shared. There's also an approach where you can do that more explicitly, like you can have control over when the data get moved, right? So that is, again, we will learn in the more advanced topic. So that's where we will be looking at both those implementations. Right?
Awesome.
Okay, so let me go back to the dev cloud. Right?
Before you get going, could people just like throw a thumbs up or something in the chat to let us know that you're caught up and dev cloud's working for you? Or do we need to give you another minute or so?
Yeah, so let us know if you are running into any issues. So I put the link up there. So even if you haven't registered, pre-registered, so you can register. It only takes a minute to complete basic information, and then you will be able to just click on getting started, and then you should be able to click on this option called Launch Jupyter Lab. And that will open up an interface like this, right? And the first thing we'll do is we'll click on this terminal here. So this will mainly give you access to like a command prompt. So it should look something like this, right? So let me know if you are able to get this command prompt running, and then I will paste a command to actually copy some data oneAPI. So this will copy the workshop content from our data directory into your local directory. So just paste this into your terminal, and then this should actually copy the entire workshop content to your local directory, right? So if you run this, you should see a folder called CPP SYCL Introduction on the left-hand side. Right, so once you have this directory, so we'll go inside that directory, and then you will see the Jupyter notebook file with this IPYNB extension, right? So you can double click on this, and this has all the training material for this introduction topic that I just did. Yeah, I see a comment that the Jupyter Hub server is very slow. Yeah, it usually the very first time you register, I think it's copying all the training content to your local directory, so it might take some time, but eventually it should start up. Where is the launcher again? So in the website, after you log in, so if you click on Get Started, right, and then scroll all the way to the bottom, there's an option called Launch Jupyter. Okay. And this entire training material is also on GitHub. I'll paste the link, and then you can get the entire thing onto your local machine as well, right? So with that, so let me go over this hands-on workshop, right? So you can see that this notebook here has all the information that you just looked in the slides about why offload computation to accelerator, what is SYCL, and then we'll start off with the source code, right? So I also have this C++ code here, the same thing that we looked at, the 3 steps, right? We initialize a data array, and then we do some computation on the CPU, and then we print out the result, right? So in Jupyter Lab, the way this works is this has a coding cell. You can actually edit the cell to whatever you want, right? You can change the code here. And then what this will allow you to do is if you run this cell, that is just click anywhere in the cell and hit the play button here, this will just save the file, right? So if you made any changes, so you don't have to make any changes. So we just save the file. And then there's an option to, there's a script here that will automatically compile and run the code for you. So to do that, you would just click on this cell and then hit the play button again. And then this will compile, and then it will give you the results. So you can see that it's printing out multiples of 5. That's why, because that's what we did, right? So we just have 16 elements here. This was initialized from values of 0 through 15, and then it's multiplying each number by 5. So for example, if you want to change this code, you can change this 5 to say 3, and then you can say hit play again. This will save the file, and then you can run this compile script again. So if you compile it again, so you'll see that it's all multiples of 3, right? So hopefully people are able to just play around with this one to get an understanding of how we will be executing code on Jupyter Lab. So what this script is actually doing is just doing this line here, right? It's actually compiling using ICPX, and then it's running the resulting file. So if we want, we can actually look at what's inside run CPP compute. You can see that it's setting the environment variable. It's compiling the file, and then it's just running the compile. If there are no errors, then it will just run this a.out. Okay, so instead of typing that command one by one, we've just written a script that will do everything, and then the script is what we are executing here, right? So if you want, you can actually go to command line and do the same thing manually, right? So if you're used to running on just command line interface, then we can go into the directory, which is C++ SYCL introduction. And if you look at all the files here, you'll see that our code is actually in the lab directory, right? So if you want, you can view the code using the editor, just cpp compute, right? So we can see the file here. And then if you want to compile this, you can just do ICPX and then specify the C++ file, right? So this will just compile, and then you can do a.out, and then this will give you the result, right? So if you want to go and change the code again, right? Let's change this back to 5. Save the file. Now I can compile this again, and this will give me the output, which is now multiples of 5, right? So hopefully people are able to run this and then see the results. So if you have any questions or stuck anywhere, please post something in the chat window and we'll help you out there. So now that you know how to compile and run this C++ code, so let's look at how to run the SYCL equivalent of this, right? So here you can see the second example that we have. So we've done the 3 things, right? Selecting a device, that is selecting a device here. And one more thing we have done here is we are actually printing out the device name that is being selected, right? That's the first step. And then we can see that we've changed the memory allocation type. We've changed from a direct float definition to using malloc_shared. And then the third thing we've done is we are submitting the actual computation by using this single task, right? So we've done everything that's necessary for a SYCL application. So we can also try to run this one. Right, so we will save this file, and then we will click on this run script again, and then hit the run button. And then we're running this slightly differently. You can see that I see another question on the chat, and this hopefully answers it. If you run the script directly, it will just run on the node that you have, which is just a CPU node. If you use this Q script, Q.sh script, right? So this will actually make sure that your job gets submitted to a node which has a GPU on it, right? And this usually takes some time because it has to go and find a available node, and then it will execute on that device, and then it will run, right? So you can see that after a few seconds, I was able to get the output, and you can see that it prints out the offload device name as Intel UHD graphics, and you can see the actual output multiples of 5 being printed out, right? So if you want to try this on command line, you can do the same thing. Right, so you can say ICPX, and then we use the SYCL flag. And in this case, we will use compute, right? So this is the file name, the SYCL offload, compute offload. So this should compile the code. And then notice that if you try to run this code, it will actually run on the CPU, right? Because this machine that we are trying to run on, if you look at what are the different hardware available, you see that there's only a CPU available. There is no GPU, so that's why it ran on a CPU, right? Because if you look at the code, we had selected the device selector as default. So this tries to find a GPU. If there is a GPU, it will run on a GPU. If not, it will run on a CPU. So that's the reason this code was run on the CPU. So how do we run this on GPU, right? So that's when you would use this CUDA.sh script, and then we will pass on the actual compile and run script. So if you look at the compile and run script here, you can see that all it's doing is initializing the environment variables. It's compiling the file, and then it's running, right? And you can, instead of doing manually, you can try this run script. And this will do the same thing. It will compile and then execute, and you should get the same result, right? Again, it's running on this local machine, and that's the reason it's running on the Intel Xeon CPU. So if you want to run it on the GPU node, use this q.sh script first, and then pass the run script, right? Q script, and then the run script, and this will it'll take some time, right? So it'll try to go and find a free GPU node on the Intel Dev Cloud, and then it will submit this script to that specific node. It will run there, and then the results are copied back. So it can take anywhere. The script we have written, I think it times out after 60 seconds. Usually if it times out, it means that the GPU nodes are busy, it's not able to find, but usually within a few seconds, you should see the result, right? So this time when we actually use the Q script, you can see that the offload device was actually an Intel graphics device, right? So hopefully you're seeing the same results on your end, so you can try that. So this is useful if you're doing a direct SSH connection to the Intel Dev Cloud, so you can see how you can run the same code on in command line. But for this training purpose, I mean, going forward, we mostly will be trying to run the code on the Jupyter interface, which essentially does the same thing. Because when we use this exclamation symbol, this gets executed on the bash, right, on the terminal, and then it prints out the result. So that's the second example, right? So and then we learned about the process, right, of device selection. We looked at how to specifically do GPU selection, CPU selection, and then currently we're using default selector. So if you want to see what's the difference between GPU selector and default selector, so we can try to do that change here in command line, right, to understand. Let's go to lab, SYCL compute.cpp, right? So you can see that here we're using default selector, right? So let's say I go and then change that to GPU selector. I'll save the file, and then let's compile this one. So let's compile. So before we run, so let's look at what machines we have on this system here. Right, you can see that there is no GPU on the system, but we've asked the SYCL code to run on GPU. So if you try to run this one, so you will get an error, right? So you'll get an exception thrown saying that the requested device was not found. So that's the main reason we actually use default selector instead of using GPU selector, so that in case you run the code on a system without a GPU, it will at least run and give you the result instead of just failing that the device was not found. So that's one of the reasons in most of the SYCL code, you'll see that the queue is just defined as plain queue like this here, right? Which means that it's using a default selector, which means that it will run on a CPU or on a GPU if a GPU is available. If not, it will run on CPU, right? And we learned about memory allocation and then submitting a task. And then finally here, we have another example, which is mainly replacing that single task with parallel for to get parallelism, right? So the three examples that we looked at in the slides, so you can execute and then try those out. So again, I think even this one should get you the same result, multiples of 5. So let's wait a few more seconds and then we can go to a lab exercise. Right, again, you see that this was offloaded to a GPU and then we got the results, and this time it was using parallel for, right? So the next one, right? So at the end of each one of these exercises, we have a lab exercise where you will have to complete some code and which will give you the result. So here mainly we have a C++ code to do vector addition. So what vector addition is doing is there's 3 arrays, A, B, and C, and we're initializing values of A and B, and then we're calculating C equal to A plus B, right? So you can see the code here. We're just including IO stream, and then you can see that there are some steps here asking you to write your code. But as it is, you can see that it's just initializing a value. It has like 3 arrays, A, B, and C, and we're initializing A and B to 1 and 2. C is initialized to 0, and then we are doing some computation using a for loop, and we are doing C equal to A plus B, and we are printing out the result. So if you try to compile this as it is, you will see that it'll give you the result, but it's actually just running on a CPU because we haven't used anything SYCL specific here, right? Right. So you'll get the value as 3, which is 1 plus 2, right? So let's do this lab exercise. So all you have to do is we'll give you about 10 minutes to do this lab exercise. So just look at the code here where it says like step 1, step 2, step 3, and step 4, right? So you have to write some code here so that this code will now run on the GPU instead of CPU, right? So let me see if you have any questions. So the result, I mean, the solution for this should be up top, right? If you scroll up, we've learned all the concept that you should use to like complete the code here, and then you will get the right result, but this time on the GPU. So go ahead and then use this instruction and then try to complete this exercise, and then we will proceed. So let's look at step 3, right? So step 3 is mainly allocating the memory so that both host and device can access, right? So how do we do that? So let's go back and see, right? So one of the solution here, you can see that the way they've allocated memory is using this malloc shared. So I can just copy this line of code. But here in this example, we have to allocate 3 allocations, right? Because there are 3 different arrays. So I can just paste this 3 times, but instead of data, this will be A, B, and C, right? And you don't need this regular float definitions anymore. So I'll just comment that one out. So, so this is done, right? And then the final step is submit computation for the offload device, right? So how do we do this? Right, so in this case, 2 ways to do it. If you want, you can use single task, but then, bonus points if you used parallel for, right? So if you use parallel for, you have to remember to get rid of this for loop here and then use parallel for. So just go back up and then you can see how parallel for syntax actually looks like. So we just copy this thing. Come back here, paste the parallel for. We don't need the for loop anymore, right? So we'll get rid of that. And then close it. And then always remember to add a wait there, right? So we have to wait until computation is complete on the GPU before we print out the result. So that's your that should get you the output. So you can compile and run. So what I'll do is I'll hit the play button here. So you should see that it overwrote the existing file, and then you can compile and run, right? So just run that cell again. So this should submit to a GPU, and then we'll give you the result. Right, you can see that the result, so it's saying it's offloaded to a GPU, and you got the result, vector add result of 3, which was 1 plus 2, right? So this is a pretty simple lab exercise. So hopefully, if you know how to do these 3 things, you can pretty much offload any C++ code that you have, and you can offload it to a GPU and then test it with the SYCL compiler, right? So we'll learn more to this one. So there's actually one more step that is recommended for you to do, since we've done allocation here. So this wasn't in any of the examples. So it is. So we do have to feed the allocation. So the way we would do is like use SYCL free, and then E comma Q. So Q, it's same as the regular C++ free that we use for mallocs, but here, since it's for the device, we have to pass in the Q parameter. So this is something to make the code complete. You can do this one, right? You free all the 3 allocations. So use SYCL free. So this is the completed code, right? So in case you're looking for the actual solution, so you notice that all the code that you're editing is in the lab folder here, lab, and then the file name. So the lab folder is right here. So that's where your modified code will be stored. There's also a folder called source, right? So it mainly has a copy of all the original code. So in case you do make changes on this notebook, you'll have the original code here to refer back to. And the solution is actually in the source folder, right? If you click on the solution file, so the completed code, if you're looking for the steps, it's actually in the source folder, right? So hopefully, so people were able to run this lab exercise and are getting the result. If you have any questions, please drop it in the chat. So if not, I will move on to the next topic that I was going to cover, which is more detailed concepts of SYCL programming. So let me share that screen. So now that we know the very basics of SYCL, right? So let's try to understand more in depth about SYCL programming. So in this, by the end of this module, you will be able to compile a SYCL program. So you'll be able to explain some of the SYCL fundamental classes. So we'll try to use device selection. We'll also learn about what is unified shared memory and then buffer memory models. So this is something new you will be learning here. And then this thing you've already done, which is you'll be able to write a complete SYCL program that offloads computation to accelerator. And then finally, you'll be able to use the programming capabilities to use the low-level hardware features, right? So these are the main learning objectives. Okay, so before I go, I just saw a question popped up here. The question is, if I launch 2 tasks in 2 different queue, one on the CPU and one on the GPU, and they access the same array, see in the example, is there a race condition, right? So mainly, if you are to submit 2 different queues, right? So if you're using 2 different queues, then you're obviously accessing 2 different memory allocations. So you can't really access the same memory. So let me go back to the example here. Right, so in this example, so if you have to create 2 queues as an example, right? So you would have created something called a CPU selector, and then you create another thing called, let's say Q underscore GPU, and then this will be a GPU selector. So if you have 2 different SYCL queues, the allocation that you're creating is also requires this queue parameter, right? So this allocation now data is actually only available for the CPU, right? So if you want the same data allocation, you do have to create a different allocation and then create another allocation called GPU Q underscore GPU, and that's the data that's accessed, right? So you have to make another copy of the same data, and then you can have both the accelerators access that. So you won't really run into race condition if you're using multiple devices. So hopefully that answers the question. Right, so let me jump back to the slides here. So C++ with SYCL, right? So mainly it will enable you to program for heterogeneous hardware with from different vendors. So it's mainly a single source that, as we looked at, which will enable you to write host and kernel code to offload to GPU, CPU, FPGA, or any other accelerator. So SYCL is mainly based on open standards. It comes from the same standard that developed the OpenCL standard, the Kronos group, right? So mainly there is a oneAPI implementation of SYCL. So this is mainly C++ SYCL and some extensions. So it's standard based, and it's open source. So anybody can actually contribute or submit issues to the compiler. So it's all available on Git. Let's look at a simple example. So I'll go through this fast because we've already looked at basic examples. So you can see that both the host code and the accelerator code will be in the same source. We've used created a queue. We've done some memory allocation, and then we submit the kernel for offload using Parallel 4, and then the code inside of Parallel 4 is what is the code that executes on your accelerator device, right? And we wait for the completion, and then we can print out the results. Right, so how do we compile a SYCL program? Initialize the environment variable, and then we use the ICPX with the fSYCL flag, and this will compile the SYCL application, and you can run it on any device, right? So with that basics in mind, so let's look at some of the important classes in SYCL, right? So the first main important thing is the queue, right? So this is something that's used in every single SYCL program. It's the first step where you create a queue. If you don't specify anything for the queue, it means that it's a default selector. So it will run on a GPU. If there is no GPU, it will run on a CPU. And the queue is mainly used to submit kernel, mainly the code that executes on the offload device. So you can use either queue.submit and then put your entire kernel code in there, right? And we will look at different ways to write the offload code. And there's also a device class. So mainly a device represents the capabilities of an accelerator. So let's say you create a queue, you can get the device by just doing queue.getDevice. And once you have the device, you can get all the other parameters of the device. So as an example, you can get the device name, right? So you can also get the device capability. How many compute units does it have? How much memory does your device have? So all that information can be queried once you have the device available to you, right? So this is mainly useful. Let's say you're doing some memory allocation, and then trying to store some local memory. So it's a good idea to actually see how much memory your device has and only allocate so much memory. So that's when you would use this device class to see what is your device capability. Right, and the next step is choosing where to run your code on. And this is what we looked at in the examples before. You can see that there is various ways you can create your queue and do device selection. So there's the CPU selector, which will use CPU selector for offloading. If you use GPU selector, it's a GPU accelerator, any other accelerator other than like CPU or GPU. There's a default selector. These two lines are default selectors, which will allow you to select a GPU in case it's available, if not CPU, right? And then there's finally something called the aspect selector. So this is something new that was added in the latest specification. This is something if you want to select a specific type of device based on a feature inside that device, right? So in this case, we are saying aspect selector, but the aspect needed is an image, right? So this mainly says that image is like a device that supports image processing, like so you can say this one. So this will select either a GPU or a CPU with which has the image capability as an example, right? You can also have other aspects like does it have local memory support, right? So that's another aspect, or different other hardware features. The second example here, it's mainly saying you can put multiple aspects here, right? You can say something that supports images and also has to be a GPU. So in this case, it will select a GPU that also supports images, right? So these are some of the different ways you can do your device selection. But to start off with, you can just use default selector. If you want to get more broader support to different vendors, you can also write your custom logic, right? The example here, what it does is it sets priority based on your own logic. In the first thing here in this example, it's trying to find a device named Xeon, right? So that gets the highest priority. So if your system has a Xeon processor, it always runs on that. And then the second priority is given to GPU. If there's no GPU, then it finally runs on any CPU that you have, right? So you can change this to whatever you want for your case. Let's say you have a code written and you are targeting 5 different systems, and 5 different systems have different configurations. So in that case, based on your environment, you can set different priorities so that your code always runs the fastest, right? So this is something to keep in mind as you get more advanced into SYCL programming. Okay, and then we have the actual kernel, right? So we have a queue created and you submit the kernel. We looked at this one, the code that actually runs on the device. That's what we refer to as a kernel or a kernel submission. So this piece of code you'll be seeing in almost all the examples. Right, so let's look at how a SYCL application is constructed. So mainly there is the application group scope or the command groups scope, the code that executes on the host, and then there's the kernel scope. This is the code that executes on the device, right? So the kernels can be, there are different kinds of kernels. We have the parallel kernels. We looked at this one. A simple for loop in a CPU application can be written using parallel for, and when we are trying to offload it to a GPU or any other accelerator, right? So mainly it's same as a for loop, but then each one of the items gets executed in parallel. So you have all the parameters. The first parameter specifies the total number of elements, and then the I is the index so that you can iterate through it, and then there are 1024 elements depending on the hardware. All 1024 or some of them will be executed in parallel in a few iterations, right? So that's what the offload capability does. So there are various types of parallel kernels. We've mainly looked at this basic way of writing a parallel kernel where we specify the entire range and then we specify the ID or the index, right? You can also have another syntax where you specify the range as well as what's called an item. If you have the item, you can query for more properties, like you can get the index from it, and then you can also get the entire range. We will look at examples where these two are used. And then there is also something called ND range kernels, right? So usually when you start writing code for GPUs, we group the execution. So if there's a very large data set, then we group it into smaller groups, because smaller groups are executed on different compute elements on the GPU. So for that case, we will look at examples where we will group the executions into smaller groups and then specify the group size and so on, right? So where it's helpful is you can see a very basic GPU architecture here, where there is a bunch of these blocks called subslice, or in the newer architecture, it's called the XE cores, right? So there are many XE cores, and when we group executions, each of these groups will map to each one of these XE cores or subslice. And if you have multiple groups will be scheduled on multiple EUs, and then all of those can be executed in parallel instead of having just one large group. If you chunk it up into smaller groups, this will enable parallel execution, and you can get better performance. And that's what we will mostly be learning when it comes to optimizations, right? So the syntax for that is, if you remember in the previous case, instead of specifying this entire ND range, we specified just one number, right? So in this case, when we use ND range kernels, we will specify the entire range and also specify the group size, right? So in this case, there are 1024 elements, and then we are dividing into blocks of 64, and each 64 will be executed on each of those compute blocks on the GPU, right? So many of those blocks can actually run in parallel, and that's how you would accelerate your code. And coming into memory models, right? So in the previous examples, we just looked at the unified shared memory model, which is very similar to like pointer-based memory, right? But the SYCL specification also has something called buffer memory model. So this is mainly, well, some cases when you have 2 or 3 dimensional data, it might be easier to represent that data using this model. But both the memory models, at the end of the day, it's using the same driver APIs to actually copy the memory and then set the memory and so on. It just gives you 2 different memory abstractions to write your code in. You can decide which one you want to use. If you're more familiar with the C++ pointer-based memory, you can continue using unified shared memory, or you can also look at the buffer memory model if you want to. If you're dealing with more of 2 and 3 dimensional data, it might make representing the data easier, but there is no functionality bias. You will be able to accomplish functionality using any of the 2 memory models, right? Same thing with performance. I mean, you will get almost the same performance whether you choose buffer or unified shared memory. It's just programming style is different. So just to look at the comparison between buffer model and unified shared memory model. So let's look at these 2 examples here. So you can see in this example, we have a cube created, and we have a vector of data of a size n, and then all of the elements are initialized to 10. In the buffer memory model, what we do is we encapsulate the data, vector data, into a buffer and create what's called a buffer here, buff. And then when we submit the kernel, we create what's called an accessor, and then accessor, we set the permission, whether it's read or write. And then in the kernel code itself, we mainly access the accessor, right? And once the kernel submission is done, you can use something called a host accessor to copy back the data, right? And then you print out the output. So it's taking the original data and then using an abstraction called buffer, and then we mainly use this accessor to modify that data, right? So in this case, it's just using one-dimensional data, but you can represent this data in 3-dimension or 2-dimension for your programming, right? So the three main unique things in this one is we have to first create a buffer, and then when we submit, we have to create an accessor, and then to copy back, we create a host accessor. So these are the three new SYCL classes that we'll be using to represent the data, right? Whereas compared to like unified shared memory, you can see that we've looked at this example. This might be much more simpler as far as coding. We're just using malloc shared, and this data will be available on host as well as on device to modify. And that you can see that the device is modifying the data, and then host is also updating, initializing it, the device is modifying it, and then you can print the data out, right? And you notice that there is a wait statement here. This will mainly wait until the execution is complete, so that when you access the data here, the memory is copied back, right? By the compiler does all the implementation. But whereas if you look at the buffer example, we're not using wait there, but instead we're using host accessor. This will act as wait, right? So this is a blocking call. This will wait until the kernel submission is complete. And once this is complete, then this copy actually happens and then is available to you. Right. So this is the next step, right? So we talked about this. So we looked at unified shared memory using this malloc shared. But then if you want to have more controlled movement of data, you would use this malloc_device. So this is mainly allocating memory on the device specifically. And if you do that, you have to explicitly move the data from host to device. So mainly you have a, so here you can see that the data is moved from host into device, and we wait for that data transfer to complete, and then we do the actual computation. And once the computation is done, you can manually move the data back to the host, and then the data gets printed out, right? So this is more of a typical case that is used in most of the programs, because the previous method, if you use malloc_shared, all the data copies happens implicitly. You don't have control of when exactly you want to copy the data back and forth. So that's the reason to get performance, you would use malloc_device. This would mean you have to write more lines of code when it comes to like copying the memory, but then at least you will have control over when exactly in your code you're actually copying the memory, because you can get more creative by while the memory copy is happening, at the same time you can have another computation running, right? So you don't have to really depend on the compiler to do the memory copy, and there you won't have control over what else to execute when that copy is happening. So when you do it more explicitly, you can write more performant code. So this is another important class or function, SYCL function, that you will be using to write more better performant code. Right, and again, notice that each of these mem copies are like this parallel for computations. We have to use wait at the end of it. So that's what's making sure that there's no data race condition, right? Because we don't want to be computing before the memory copy is complete, right? So that's why when we say memory copy, we wait until it's complete and then move on to the next step. Right, so now that we know the two memory models, right? So how do you choose which one you want to use? So the buffer memory model, it's mainly, a new concept. So there might be a learning curve before you can learn all the different concepts before you write code. but in some cases, when you're dealing with 2 or 3-dimensional data structures, it might make writing the code easier or writing the computation easier. If you use USM, porting any existing C++ or CUDA code will become very easy because C++ and CUDA will uses something similar way of doing memory allocation, so it might make it easier to migrate your code. The other thing is you have to set up your kernel dependencies explicitly, and it's mainly there's shared allocation and there's device allocation. So if you use shared allocation, you may not get better performance, so you have to use device allocation, as we mentioned. So it's up to you to decide which memory model you want to use. Well, both are in the specification, right? So depending on what background you're coming from, C++ or CUDA, or if you're starting off from more of the application side, you can directly start using buffers too. Right, so there are more reference material and more modules that go into more in-depth for each one of these topics, like buffers and accessors. There's your unified shared memory module, and there's also graph scheduling and data management. So Intel usually has workshops that are regularly scheduled, and then we cover this in each of the 90-minute sessions that we have. So there's also recordings available, so you can always access this if you want to get more information. And the same GitHub that we posted has all the information about how to get the training material for these topics, right? So before we go into the next hands-on, I will quickly, I think, go over one more section of this one where we look at code anatomy, right? So I think we've looked at this one. So the basic SYCL code anatomy, the first step is we create a queue, which you can specify a device if you want, or you can just let the default selector. And then we create buffers for all the data that we have, A, B, and C, right? And then we submit the kernel. And inside the kernel, we create a accessor. You can see that, again, we are doing C equal to A plus B. That's why we've specified C as write only, and then A and B are read only, right? And then we do the computation, which is C equal to A plus B. And this will submit the kernel, and for each kernel invocation, each one of the n elements is invoked and then executed in parallel. And then the I is the index that will go through the entire range. Once the computation is done, the buffer gets destructed, and then the data C is available for you. Right? So mainly this code that you looked at will execute in 2 parts. One is the host code, and then the other is graph kernel execution, right? So these kernels are executed independently. So that's the reason we have to synchronize using wait. That's what we looked at. Right, so if you look at the code here, the host code starts executing, and when it comes to the kernel code here, so this part gets is asynchronously executed here. This is the kernel code, right? So and this is where you need to do some kind of synchronization. So in this case, you can see that there is a scope here. This scope will make sure that it waits until the computation is complete before it prints out the result. Right. So let's look at the what is the kernel code, right? So anything that you write inside of Parallel 4, this is the code that actually runs on the GPU device, right? Or any other accelerator you're selecting. So you can actually write the entire code just in using C++, right? And there are some restrictions about which C++ calls you can use, and there's also some library calls you can use. So this is mainly you can write your entire algorithm in C++, or there is a bunch of SYCL APIs, right? That exposes programming capabilities to access the low-level hardware. So that is what the rest of the 80% of SYCL is, right? So that's where you need to learn all that to make your code run faster, right? But for the basics, just to get the code running on GPU, this is all the basics you need, and you can write your entire kernel in C++, or you can eventually you can start learning all the other capabilities that are available in kernel code, and then you can implement those changes, right? So just as an example of the kernel capabilities, right? So we won't be going over the training for these specific topic areas, but this is something that will become very important in the future. Like I said, when Intel does the workshops, live workshops, each of these are a separate topic that we do a 90-minute session. So we can also come back and then do these trainings for you at a later time. But then, these are the advanced topics, right? So like how to use the shared local memory that's on the GPU device, right? How to use the subgroups, or you might have heard about warps in CUDA programming. So the same as warps, what we refer to as subgroups. It's mainly a group of work items that execute concurrently. How do you program using that one? This will give you significant performance. There's a bunch of group algorithms that you can directly use that are optimized to run fast on GPUs, right? And there's atomic operations, because you know that computations are parallelized. So you can, a lot of these work items that are executing can be updating the same memory, right? So that might run into race conditions. So to avoid that, we have these atomic operations that are available. That's another topic. And then there's kernel reductions, right? When you have to write code that involves any reductions, it might make the code very complicated because of the race conditions, because multiple items are trying to update the same data object. So to avoid all that, there are some reduction methods that are available in SYCL, which will help you to simplify the code when writing reductions. So these are all available as advanced topics. It's mainly used to optimize your code for performance, right? So there's also, you can self-running Jupyter notebooks available, right? So you can follow these chapters in that to get more information, right? And there's more resources that are at the end of this presentation, which I will send this PowerPoint presentation so you can get all these access to all these links, right? With that, let me jump into my dev cloud. So let me restart my dev cloud. So usually the dev cloud times out after 4 hours of logging in. So if you run into that issues, just say restart and then it will restart. So let me know if you have any questions on the PowerPoint material I've had so far. If not, I will run a couple
Hey,
more
Rakshith, there was a
examples.
question. Someone asked if there are 2 GPUs in a system, you launch 2 tasks. Do you need 2 separate queues, or can one queue address 2 separate GPUs?
Yeah, you will have to create 2 different queues. Because 2 different GPUs, there'll be 2 different memories that you'll be accessing, right? So yeah, each queue can allocate memory using 2 different queues, and that's the memory that will be accessible for each GPU. Right? So we have examples of those, and we will look at that. So let me start a terminal again. So if you just registered for DevCloud, you should already have this folder called oneAPI Essentials. So this should be pre-populated. So you can just directly access this, right? And this is the module. You'll see that we have all the advanced topic, right? The introduction through the advanced topic. And today, I think we've just covered a couple of these, right? 02, which is the program structures, and then unified shared memory, and also a little bit of buffers. But all these other topics like subgroups and local memory atomics, I think these are all more advanced topic, mostly used for performance tuning, which you can look up the Intel website for the past workshops and webinars, and you can follow along if you want more information. But in today's session, we'll mainly try to cover this program structures module. So if you open this program structure module, you'll see all the information that I presented in the slides are right here. So let's look at some examples, right? So I think we've already tried similar example for GPU selection, right? You can use this example if you want to see how your code runs when selected a GPU versus selecting a CPU. So I'll skip through that one since we've already done similar example. Let me go to this buffer host accessor example, right? So if you want to directly go to that, there's an index here, and then just click on the synchronization by host accessor. Right, so here you can see it's an example where we have a vector of 16 elements initialized to 10, and we create a queue and we create a buffer here, right? So we are not using the unified shared memory model, but buffer model. So that's why we're creating a buffer. And whenever you create a buffer, and when we submit a task, we have to create an accessor for it, right? And the accessor is what can be used to modify the data, right? So in the actual kernel call, you can see that we are updating the accessor. We are reducing each element by 2. And then once this is done, you can see that there is a host accessor. This is what will copy the data back to the host to print out the result. So if you want to run this example, hit the play button. This should save the file, and then hit the play button again, and this will compile and execute on a GPU. Like you can see the result. The result is printing all 8 because that's what we did here, right? So it's mainly showing an example how to use a buffer memory model, right, as opposed to using the unified shared memory model, right? So you can look through those examples. There's another way, right? So instead of using host accessors, you can, if you have a scope for the entire computation for the buffer, so when the scope actually ends, the data automatically gets copied back. And this example here shows how buffer destruction works. You can try that one. And let's look into this examples here, right? We talked about custom device selection, where you want to do a device selector based on certain criteria, right? So we have a few examples here where let's say you have devices from multiple vendors in one system, right? So then you can pick a specific device using a custom device selector. So in this case, we are asking it to return only if the device vendor name is Intel, right? So if you have Intel GPU and you have another vendor's GPU, and if you want to run your code on specific vendor, then that's how you can use this code, for example, right? And the second example is slightly more complex, which is mainly telling return a GPU device with the name Intel, and also it should be a GPU, right? In the first case, we are not saying anything about the type of device. So this can actually pick, if there's an Intel GPU, it'll pick a GPU. If there's a CPU, it will pick a CPU, right? So the code will run either on Intel CPU or GPU. But in the second example, we are specifying it has to be a GPU, right? So this will pick an Intel GPU. The third example is priority, right? So it's mainly first priority is given to a Xeon, second priority is given to any GPU, third priority is any CPU, right? So we have one example here, right? So which is mainly doing selecting a GPU with the vendor name, right? If that GPU with that vendor name is not available, the second priority is given to any other GPU that's available. And the third option is any CPU, right? So you can try to run this code and then see the output, right? In this case, we are actually submitting the work to an Intel GPU machine, right? So it'll obviously like pick like an Intel GPU. So, right. So the output of this one, you can see that it's printing out the name, right? So it's printing out that it's an Intel graphics device, right? It's because the condition we gave it here is first priority should be a GPU, and it should be a vendor name as Intel, right? So, so if you want, you can also change this code to play around and see if you can change that to the first priority is a CPU with Intel name, second priority is GPU. So let's see what happens if you try to run this code. So in this case, see, it actually picked a Intel core processor, right? Because we said the first priority should be a CPU, right? So you can change various options here. You can change it to GPU, and we can specify the vendor name as something else, right? We can say, let's pick a NVIDIA GPU, right? So let's see what happens if we do this one. So the first priority we're saying it should be a NVIDIA GPU. If it doesn't find that, it can be any other GPU from any vendor. The third priority is the CPU, right? So we are running on the Intel Dev Cloud, so we don't have any NVIDIA GPUs. So it should fall back to the second option and then pick a Intel GPU, and that's what's happening here. Okay? And then we have a code example here, slightly more complex code, right? It mainly computes like complex number multiplication, I think. So this is like example of large code, right, which creates a bunch of different buffers and accessors, and then a kernel computation with templates and stuff. So it's mainly for reference. If you want to, you can run this on your free time. So mainly I want to give the last 5 minutes for you to try another version of this vector add example, right? So based on the concepts that you've learned here, mainly we had this code here, which is doing a vector increment, right? So we have a vector defined, vector 1 with all values of 10, and we create a buffer for it. We create an accessor for it, and then in the kernel code, all we are doing is incrementing each element by 1, and then we have a host accessor, and then we print out the values. So let's run this code and see. So according to this code, all it's doing is like incrementing the vector with all 10s in it, right? It's all 10, and we are incrementing by 1, so the output should be 11, right? So you can see the input vector is 10, and the output vector is 11, right? So the lab exercise here is that it's mainly asking you to create a second vector, and then you have to add vector 1 and vector 2 and give the results, right? So again, like in the previous example, you can follow these steps, step 1, 2, and 3. Like I'll complete the step 1. So it's mainly saying create a second vector and initialize to value 20 and print the result. So here's the code, right, to create vector. So you can just copy this entire thing, just change this to vector 2, and it said, and you have to initialize this to 20. So we'll do that, and then we print out the results of vector 2, right? So that's your step 1. So if you want, you can save that and then run the code and see what you get. On the step 2, we created a buffer for vector 1. So create another vector for buffer for vector 2. That will be your second step. Third step is there is one vector, so you have to create the second vector. And finally, the main code is change this so that vector 1 gets updated with vector 2, right? So you can see the result right now. Input vector is 1 is 10, input vector 2 is 20, and the output should actually be 10 plus 20, which should be 30. So that should be your result. So if you complete step 2, 3, and 4, you will have the correct output. So let me put up a 5-minute timer, and then we'll come back and look at the results. And then I think we have a break for 30 minutes, and then we'll come back with the tools. Yes, so there's a question. So in the previous example, we had q.parallel4, but here we have a q.submit and then h.parallel4. Is it because we are using buffer? Yeah, that's exactly the reason, because let's go back to an example, right, which is using buffers. So this example right here, whenever we use a buffer, so we have to use an accessor, right? So the accessor is part of the command group, right? So it is defined outside of parallel4. So the entire thing has to be wrapped inside of q.submit. But in case if you're using unified shared memory, so there is no need to create this accessor. So that's why we can directly call q.parallel4. But if you want, you can also leave the q.submit as it is and then have h.parallel4, even if you're not using buffers, right? So for example, let me go back to the C++ introduction example, right? Let's say this example, right? We just have q.parallel4. So if you want, you can, this was the original syntax in the SYCL specification, right? So you can actually have something like this. This is also a correct way to write your code. Right, you can use q.submit with a handler, and then you can have h.parallel4, and then you have a wait, right? So this code will also execute fine. It will get you the same result, but it's just redundant, right? So this simplification was just added. If you want, you can just get rid of this q.submit and just directly do q.parallel4, and which pretty much does the same thing as submit, and then the actual method it's using to submit the kernel. So something happened here. Okay, so I think I haven't defined the SYCL here. Right, I think in the previous example, we had a using namespace SYCL. So that's why here I had to specify the SYCL explicitly. So hopefully this code should compile and should get you the same results. So you'll see that you'll get the same results. So if just to simplify, in case you're using the unified shared memory model, and if you're not using buffers, right? Because when you use buffers, you have to create an accessor inside of submit, but you can just get rid of this entire code and just have q.parallel4 directly, right? Just makes your code much more simpler, right? Hopefully that answers your question there. Okay, so let me go back to the lab exercise here. Right, so you've done step 1. So step 2 is like pretty easy. You have to create another buffer here. And then that is be vector 2 buffer and for vector 2. And then we have to create a second accessor here. Change this to vector 2 for vector 2 buffer, right? And then finally, you have to modify the code here so that it adds vector 1 and vector 2 together and then gives you the result, right? So you can just do vector 1 plus equal to vector 2, right? And then rest of the code should be the same. So if you run this code, hopefully it should give you 10 plus 20 equal to 30 as the output. Okay, still waiting for the result here. Okay, so there you go. So looks like the implementation is correct. You can see that the input vector is all 10s, and then second vector is 20, and then the output value is 10 plus 20, which is 30, right? So with that, we are at the end of this session. So I think we have a 30-minute break now.
Rakshith, there is a quick question there. We can wrap that up with that question. Yeah.
Yeah, so there is one question, which is there a performance difference between buffers and raw pointer APIs? Can you explicitly set which device the buffer is located, right? So let's look at an example, right? So let's look at this example. So whenever we create a buffer, right? So and each buffer is actually accessed using this accessor. So the buffer that you create can be for any vector on the host, but then when we submit a vector, we actually access that buffer using accessor. So that's when it knows that Q actually represents which device this code is being submitted to, and the accessor that you create will have access to that specific data, right? So if you had another queue submitting data, so then you have to create a different accessor, because every submission will have its own accessor. That's how it actually controls which where the data is actually located. So hopefully that answers the question. So if you look at the modules here, right? So we are accessing the oneAPI Essentials module. So there is an entire module which is focused on unified shared memory, and there's an entire module focused on buffers and accessors, which go into more in-depth examples of how memory is being accessed when using the two different memory models. So those will have more specifications. So we also have videos for these past workshops for these two modules, so you can also refer to that. But yeah, in the meantime, if you have any questions, please do ask us here. So I think right now, I think there is a break. So let me put up a timer, and then I think we'll come back in 24 minutes from now, and we will resume at that time. All right, welcome back. Yeah, so we've basically mainly covered SYCL topics today, and then the last two topics we have are mostly on the tools. So we'll mainly touch on some of the tools which we have, which will make your development of SYCL much easier, faster, and help in performance improvement. The first one we're going to start with is the SYCLomatic Tool. So mainly, so this tool will help you to migrate your existing CUDA code to SYCL and then continue with your development. So let me start with this. So I'll start with brief introduction of CUDA, and then why it is important to migrate to SYCL. So I'm not sure how many of you in the audience are familiar with CUDA development. If you do, please put up some emoji again. We'll see. Depending on that, I will, adjust my presentation. So So mainly, so let's start with, okay, so what is CUDA, right? So from NVIDIA, so CUDA is mainly a parallel computing platform and programming model created by NVIDIA. CUDA helps developers to speed up their application by harnessing the power of NVIDIA GPU accelerators, right? So the important thing is it's a programming language from NVIDIA and it's for NVIDIA GPUs, right? So why do we need to migrate to SYCL? So what SYCL is it's a royalty-free, it's cross-platform, and it's open source, right? So this also enables for heterogeneous computing, not just GPUs, but multiple architectures like CPUs, GPUs, and FPGAs, and also from multiple vendors, right? So that itself should tell you the advantages of migrating to SYCL, right? So if you look at what is SYCL. So we looked at this slide. So it's mainly open standard, multi-architecture. It gives you freedom from vendor lock-in. It's comparable performance to native CUDA on NVIDIA GPUs. It's an extension of widely used C++ standard. And then we have tools that will help you to migrate, right? So in a snapshot, so if you have CUDA application, so it mainly runs on your NVIDIA hardware, right? Which is NVIDIA GPUs. But SYCL is open standard and it supports all the different vendors and all the different types of architectures as well. So CPUs, GPUs, FPGAs, you see like Xilinx here, right? So it supports all these architectures. So this will give you freedom from any one specific vendor lock-in. So you can write your code once and then run your code on any hardware you want, right? You can always do like, architecture specific coding based on for performance tuning, but the overall application will be just a single source, right? That you can run on multiple architectures. So that's the main advantage of migrating from CUDA to SYCL. So what's the process used? So let's say you have a NVIDIA CUDA code. We take that code and then run it through this tool called SYCLomatic, right? So what this does is it just goes through all the files and then migrates all the NVIDIA CUDA APIs into SYCL APIs, and then it will give you a SYCL code base where you can read it. It also adds some comments based on whether it's like a warning or suggestion based on the hardware you're using to do some tuning or to fix some code, right? So typically this will mainly migrate maybe 90 to 95% of the code. And there is some manual changes you may have to do, right? So for all those manual changes, it does give you like a commented section within the code. So you can go and easily address those. In some cases, if your code is very simple, it will migrate 100%, and then you can just compile it using your SYCL compiler, right? So that's the fourth step. Once it's migrated, you can just build that. And then once you built it, now it will run on CPUs, GPUs, FPGAs, and any other accelerators, and also from any vendor, right? So you've gone from running on only on NVIDIA to running on different devices. So that's the main advantage. And we'll mainly be looking at this tool. As you know, there's also a compiler available from the oneAPI based toolkit. This is what we were using in the workshop earlier. So once your code is migrated, you can use the compiler to compile. And CodePlay has created compiler plugins, which will mainly support NVIDIA and AMD GPUs. So once you've migrated the code to SYCL, so you can run it back on NVIDIA GPU, or you can run it on AMD GPU, right? Or you can run on Intel GPUs, right? So it gives you the freedom to run your code on any vendor, right? So that's the main advantage of that. So just a quick comparison of CUDA versus SYCL, right? So on the left side here, you see the CUDA code. On the right side is the SYCL code. So this might be a little small, but I will display this code when I do the live workshop as well, right? So the main difference is you can see that there's a header file difference. Obviously, in CUDA you'll be using the CUDA runtime header, and then SYCL you're using the SYCL.hpp. You see that the device memory allocation in CUDA, you use something called CUDA malloc that gets migrated to malloc_device when you're using SYCL. And same thing with memory copy. In CUDA, you're using CUDA memcopy. In SYCL, you're using the memcopy method on the queue. Submitting the kernel, you can see that you just in CUDA, you specify the actual function name and you specify the block size and the total number of threads, right? In case of SYCL, we use this parallel for, and inside of parallel for, you have the actual function. Parallel for is where you specify the total number of threads and also the block size or the workgroup size. We call what CUDA calls block size is actually called workgroups in SYCL. Right, and then finally the kernel function, it's the same, right? So the actual function, the computation will be C equal to A plus B. The way you calculate the index is slightly different, but other than that, the code should be quite similar, but all the CUDA APIs are migrated to SYCL here. So this couple tables here, it gives you a snapshot about what is 1:1 equivalent between CUDA and SYCL. You can see the header file difference. In CUDA, you create what's called the stream. That is same as the SYCL queue. And to allocate memory in CUDA, you would use CUDA malloc. And in case of SYCL, you use the malloc_device. And you have the memset, memcopy, similar, right? There's equivalent APIs for SYCL. We looked at kernel function. To free the allocations, you use CUDA free, and then SYCL, you use the SYCL free. To synchronize between host and device, there's CUDA stream synchronize, and then that's what wait does in SYCL, right? And same thing for more complicated APIs. These are mainly APIs that are used in the kernel function itself. There's something called shared local memory with low latency. To access that in CUDA, you would just use this __ shared to define the memory object. And in case of SYCL, you use this local accessor. And similarly, you have like all these different API differences, right? So these are the most commonly used. So you can use this table to quickly look at what CUDA code is doing, and then you can see what the SYCL equivalent is, right? And finally, the last step here, item here shows you a library, right? So let's say in CUDA might be using the cuBLAS sgem library function. And then when you write SYCL code, you can actually use the MKL library to replace those functions, right? So there is the MKL BLAS library with gem function that you can use to accomplish the same thing. So in summary, so why do we need to migrate CUDA to SYCL? Mainly because it's open standard. SYCL is multi-architecture and supports multi-architecture and gives you performance portability, gives you freedom from vendor lock-in, and it's also an extension of widely used C++ language, right, as opposed to a proprietary language. So that's mainly the summary of this. So with that, let me show you a demo of SYCLomatic and how that can be done. So to do that, so this the actual migration you would be doing on your CUDA development machine, right? So so this won't be like a hands-on workshop. So if you do have a CUDA machine, if you have access to a CUDA machine, you can try it out during the workshop. So there are mainly 2 steps involved in migration, and we will be doing the first step on the CUDA machine, which is migrating from CUDA to SYCL. And once it's migrated to SYCL, we can run that code on Intel Dev Cloud on various different GPUs, CPUs, and FPGAs, right? So to go over that, so let me bring up the workflow that's involved in the migration, right? So so we mainly looked at this flow where we start from CUDA code, we use SYCLomatic, and then we build it and deploy it to various devices. So the prerequisites for this is you need to have access to a CUDA development machine to mainly do the migration. And once that is done, we can run the code, the resulting SYCL code on Intel Developer Cloud. So this is the step we usually use for migration. Step 1 is on your CUDA development machine. So we will copy the CUDA source, right? We will install SYCLomatic Tool, which is only about 20 megabytes. It's available on GitHub. And then we will use the SYCLomatic Tool to migrate from CUDA to SYCL. And once that is done, we can log into Intel Developer Cloud, and we can transfer the code that was migrated to your Developer Cloud, and then we can compile it there, fix any errors if there are errors, right? And once you fix the errors, you can now run it on GPUs and CPUs to do functional correctness, right? And then yeah, if you want, you can optimize your code for performance. So, that's like a big task. So if you're interested to run the SYCL code, you can run the same SYCL code on NVIDIA machine, right? So for that, you do need to install the compiler, because on your CUDA development machine, you won't have the SYCL compiler. So you have to install the compiler there and also install the NVIDIA plugin from CodePlay that I was talking about. And then you will be able to compile the SYCL code on NVIDIA machine and then do a performance comparison, right? So let me show this demo, right? But if you do have access to a CUDA development machine, you can do it live as well, right? So, so let me bring up my terminal. Let me make the size a little bit bigger. Okay, so this is my NVIDIA machine, so I can show you the configuration here. So you can see that I'm on an NVIDIA machine, which has a Tesla P100. I have CUDA 11.7 here, and I have the driver version here, right? So I can also check my CL info. And this will show you what system I have. You can see that I have an Intel Xeon processor with the NVIDIA Tesla P100 card, right? So this is the system I will use to migrate. The reason you need a CUDA development machine is because to do the migration, the tool actually relies on the CUDA header files that are included. Those are referred to while migrating each one of the CUDA API calls. So the first step we will do is install SYCLomatic Tool. So you can just create a folder called SYCLomatic. So right now I have something in it. So let me just remove all the contents of this one and show you how the installation can be done. To do the installation, I would let me go to the website and then pull the tool. Okay. The screen a little bit bigger. And so what you can do is you can just Google for SYCLomatic. And the first link that will come up is the GitHub repo for SYCLomatic. And if you click on tags, and then you can see that there's a release that's created almost every day. So you can pick any one of the release. So what you can do is when you click on that, if you want, you can change the date. I know there's a stable version. Let me go to that one. So for every release, you'll see that there is a different Windows release and Linux release that are created. So all you have to do is just right click and then copy the link address to it, right? And then we will go back to the NVIDIA machine here, and I will just do a wget and then paste that link from GitHub, right? So this will just copy that entire zip folder, Linux release, and you can see that here. And once you have it, just unpack this one using the tar command. And this should unzip all the files, right? So it's only about 20 megabytes, and then it has some binaries in the bin folder. You can see, right? C2S is the main binary we will be using, and there's also this tool called intercept build, which we will also use to migrate to larger projects. And then this also has some header files. These are mainly helper functions to make the migration faster, which mainly is like a wrapper to the SYCL calls. So this tool the entire tool is only 20 megabytes. So when I say install, we're not really installing, we're just unpacking into a directory. So it doesn't really interfere with your CUDA development machine. It's just a static tool that will help you to migrate. Okay, so let's take an example, right, to migrate the code. So I have an example here in my test directory here. So I have a vector add code, which is CUDA code. A simple CUDA code here, which has a simple kernel, which does C equal to A plus B. And the actual code, you can see that there are 3 vectors. A is 1, B is 2, and C is initialized to 0. And then you have 3 CUDA malloc allocations here. And we copy A and B to the device. And we run the kernel code, which will do C equal to A plus B. And C is then copied back to the host, and then it's printed, right? And then finally, we free the allocation. So if you're looking for this code, if some of you are trying it on your CUDA machine, it's actually on the GitHub. I will paste the actual link. If you go into direct programming, SYCL, Jupyter, and CUDA to SYCL migration, there's a CUDA folder here, and there's the vector add example here, right? So let me paste this link into the chat. Right, so this is the same CUDA code I've copied to my CUDA development machine, the vector add code. Right, so once you have inspected the code, so let's say you want to migrate this code, right? The tool is called just C2S, that's the SYCLomatic Tool that you install. So just verify that you're able to access this one, right? You might have to set the bin path to export this path to access it from anywhere, but this is the tool. So if you want to look at command line options, you can just type in the help, which will do C2S. Yeah, so it will give you all the different options that you can run. So the way you would migrate the code is, so you have your CUDA file right here, just do C2S and then specify the CUDA file name, right? And if you run this, you will notice that it said something like it created output folder and it processed this CUDA file, right? And then it's just saying, just refer to this file if you want to understand all the warnings. So if you just do ls on this one, you'll see that there's a new folder created, right? So let's go into that one. And then inside that, you will see a C++ version of the same code, right? So just we can check that file. And if you look at it closely, you'll see that all the CUDA APIs have been migrated to SYCL. So instead of including the CUDA header file, it's now including the SYCL header file, and it's also including this dpcd.hpp. So this is the helper function that's used to migrate. It's just like a library wrapper. And you will notice that the code has now included a bunch of these SYCL APIs, like SYCLQ is created here. So instead of using CUDA malloc, it's now using malloc_device, which is SYCL, right? And same thing, instead of using the CUDA way of submitting the kernel, it's now using parallel4, right? So all this code is automatically generated for you, and it's using memcopy to copy back the memory. And then you'll notice that it prints out the output. So the C++ code will remain the same. It's just all the CUDA APIs are now migrated to SYCL. Right. So once you have this SYCL code, you notice that this is also using that dpcd header file. So if you are interested, I mean, it's usually a good practice to actually include that whole header file as part of the migration. So what you can do is, so let's say, let me migrate this code again. So you can actually specify this option called use custom helper. So this equal to all. So what this will do is it will include all the header files. So your entire project can be copied over to a different system. So if you do run that, since we've already created output directory, so we can specify a new output directory called outroot, and then just call it like SYCL output, maybe, right? So if you run it again, you'll again see a SYCL output directory created. So let's go into that. And now you will see that it's created the migrated file, and it also has an include file, right? So if you look at the include file, you'll see that include folder, you'll see that there's the dpcd header, right? So and that's mainly used by your migrated SYCL code, right? So all these header files, custom header files, are now part of your project, right? So how do you compile this, right? So all your files are here. So if you want to compile this one, you'll have to use the ICPX, the SYCL compiler, use the FSYCL flag. You can specify that you have extra include folder here, and then you can say use vector head. Right, so that's the file you're trying to compile. So let's compile that. And looks like it compiled. And if I run this output, you'll see that you're getting the actual output 1 + 2 = 3, right? So this code, but how do we know which device it's actually running, right? So if you want, you can go in and then add the line of code, which will print out the device name. So that can be added right after this line here. So let's go here and then just add a simple printout. And I'll call it offload device. And I will print out the Q_cd1 is the queue. I can do get device, get info. And you actually specify the parameter you want to print out. So you can say SYCL info device name. Right, and then I'll just add a line break here. So hopefully this should print out before printing out the output. It'll print out the offload device name. So let me compile this again. So let's run it again. So now you notice that the code previously, the CUDA code was running on NVIDIA GPU. So now once we migrated the code, it's now running on Intel CPU, right? So we can also make the same code run on a NVIDIA GPU. So for that, you have to compile it with different flags, right? So we looked at that slide. So let me pull that slide back up. Okay. Let me pull up that slide to show where right. So if you want to compile it for just Intel CPUs, that's CPUs and GPUs, we did this one, right? So now if we want to compile it for NVIDIA GPUs, so we can add this FSYCL target NVIDIA CUDA, and then that will compile it so that it can be run on NVIDIA GPUs, right? So let me bring up the terminal again, and I think I should have this command. Right, so this is the command. So I have a clang ++. I provide this FSYCL flag, and then I provide this FSYCL target and specify this NVIDIA, specifying that it should compile for NVIDIA, and then specify the include file, and then also specify the C++ file, right? So this is the migrated SYCL code. So if you run this one, you can see that the Clang is actually using the CUDA backend. And then now if you print out the output, now you will see that the same SYCL code was actually run on the NVIDIA Tesla P100, right? So if you compile it without this NVIDIA flag, it will compile for Intel CPUs and GPUs. So if you take the same code to DevCloud, and there you can actually run it on Intel GPUs as well, right? So mainly this SYCLomatic will help you to easily migrate your CUDA projects to SYCL so that you can now run it on different GPUs, right? So what we looked at right now was only a single file, a very small CUDA application, right? So you can also use SYCLomatic to migrate much larger projects. So we have quite a few examples in GitHub, which we have migrated from the CUDA GitHub samples repo itself. So I can show you some of those examples. So I have the CUDA samples repo where they have a bunch of different examples based on the different techniques, right? So let me go into this concepts, and there's a bunch of examples here. So you can try any one of these examples. So I'll try this sorting networks example, right? I'll remove this folder, right? So you can see that in this folder, there are a bunch of CUDA files, right? Is because this example has the kernel code and then the host code separated. So you have a main.cpp, and then you have this CUDA file here. You have another CUDA kernel file, and then you have a couple more header files, and then another C++. So it's a large project, and which also includes a bunch of other libraries and so on. So when you have a large project like this, it's usually all tied together using the make file, right? So you can use the make file to generate a database of all the files that are used in the project, and that you do that by using this tool, which is part of SYCLomatic called intercept build, and you just say intercept build make, right? So if you do this, what it does is it just generated this file called compilecommands.json, right? So if you look inside compilecommands.json, it's just a list of all the CUDA files that are used in the project, right? So it just made a database of all the files basically that need to be migrated. Now you can use the input of this compilecommands.json to migrate all your CUDA code to SYCL. So the way you would do it is again use this C2S, use -p, and then specify the compile commands file. We'll again use this custom helper to include the include directory. And then this project also includes a lot of CUDA dependencies that are in the common folder. So there is a way to specify the root where you have all the common files. So it mainly looks at all the files starting from the root, starting from 3 directories behind, right? So if you run this code, I think this code should actually migrate all the files for you, right? So you'll see that it's going through line by line, and you can see that it generated a bunch of warnings, right? So now if I look at the directory, you will see that there is a new output, dpct output that's created. So you can go into that folder and you will see the same structure of code, right? There's an include file, there's the common CUDA files that are included, and the actual sample code will be included here. So you have, if you go into this directory, you'll see that all the CUDA, when you had all the .cu files have been converted into dp.cpp, right? So mainly the CUDA APIs are migrated to SYCL APIs and corresponding files are created. And all the dependencies are also automatically linked. So once you have your source generated, so again, you can just compile this using the ICPX compiler. So I'll use that, and then I'm going to include the include folder. I'll also include the common folder. We saw 2 folders in there, right? And then we will compile all the CPP files in the current directory, which is all these files here, right? We also, included the 2 include files, and then hopefully this should compile and give us the output. Right, so it's compiled, and then we can check the output. And you'll see that it mainly gave you the output. It's giving some data about the average time it took, the throughput, number of elements it processed, and so on, right? So this is, I think, using some kind of sorting algorithm. And we mainly migrated from CUDA to SYCL. And then once we have this code, we can run it on all the different architectures from different vendors. So if you want to inspect some code, you can go into this main.cpp, and you will notice that it mainly replaced the CUDA runtime with using the SYCL and then the helper files in dpct, right? And the other helper files have also been migrated. And you will, if you start inspecting the code here, you'll notice that it gives you some warnings about if it thinks that some of the migration is not done correctly, or if it thinks that something that needs to be reviewed again, right? So anytime there is a dpct comment warning, it's just for your information to look through the code and then see if there's any changes that are required. You'll see that all the CUDA malloc calls have been migrated to malloc_device. And let's look at an actual file which had the CUDA code, right? The kernel code. So if you look at this file, you will see that you'll see more warnings here, right? So one of the warnings you'll often see is consider replacing the SYCL barrier with local space, right? So it's mainly asking if you think there is no global memory access, then you can specify that this barrier is only for the local space, right? So it mainly helps you to give you better performance. If you look at other kernel submissions, depending on the hardware, the maximum workgroup sizes might be different. Based on that, you'll have appropriate warnings, mainly asking you to check the code. But by default, you can always try to compile it. If it compiles 100%, and then if it's giving you functional correctness, that's a good sign, right? You can proceed to tuning your code. If you see some errors, you might have to manually find replacements for a specific CUDA call and then migrate it. I mean, in some cases, yeah, the performance out of the box may not be the greatest, so you might have to do some tuning using manual code. So that's basically the demo of using SYCLomatic. If you access the Jupyter notebooks that we have, so the notebooks are actually right here in the same link that I sent you. So all the training material, right, for SYCL and the Jupyter notebooks are on the public GitHub in the Jupyter directory, this path right here. So the CUDA to SYCL migration training topics are right here. And you'll notice that we start off with introduction and then we go into quite a few examples of migration, starting with the most basic one. I showed you the sorting networks, and then there's a more complex example, Jacobi algorithm. And there's also a matrix multiplication using the cuBLAS library, right? So it all shows you step by step how to migrate your code. So I can open up one of these example here. So you can open this interactively on Jupyter if you want, and it mainly gives you the steps, right? The migration process. First step is we analyze the CUDA code, and then second step is we migrate CUDA source to SYCL. This is using SYCLomatic. And then once we migrate it, we analyze and then compile the SYCL source, and then we manually optimize it, right? So it mainly shows you the step-by-step instruction how to do it, right? Starting with SYCLomatic instruction, where to go, get the latest SYCLomatic, use wget, unpack it, export the path, right? Once you do this, then you can follow the steps to make plain, intercept, build, make, and then use the SYCLomatic command to migrate the code, right? And once you have the code, you can compile it. It shows you how to compile using command line, right? And then it shows you how to fix certain parts of the code. So following this self-learning tutorial, you will be able to learn how to migrate an existing CUDA project into SYCL project. And now you can run it on different hardware, right? So you can also access this training on Jupyter. I'll paste the command if you're interested in looking at this at a later time. oneAPI workshop, CUDA to SYCL migration. If you run this command, this will copy the latest tutorials and notebooks into your data directory. So I'll add this in the chat. And hopefully that will help you to get started with CUDA migration. So that's all I had about SYCLomatic. So let me know if you have any questions. If not, I will just go over a couple more tools that we have that will help you for your development and to do performance tuning. Like I said, again, each one of these topics, they have much more detailed webinars that we've done in the past that you can refer to. So mainly I will go over the Intel Advisor and then the Intel VTune Profiler tools. Let me pull up my slides here. Right. So mainly we'll be looking at this Intel Advisor tool and then also the Intel VTune Profiler. So mainly the Intel Advisor tool, it has two functionalities that are mostly important. One is called Offload Advisor and one is called roofline analysis. The Offload Advisor is what you can use to mainly find out which section of C++ code you can offload to GPU and get better performance, right? Because usually if you have a code that's running on CPU, there is some effort to migrate it to run on a GPU. You have to learn SYCL, but before doing that, you can actually analyze the existing code and find out whether it's even worth it for you to migrate anything, right? So it will give you a simulation of how much performance you would actually see if you migrated a specific code to run on a GPU, as an example. So that's what Intel Advisor will help you to do. So mainly what it will do is like you can input C++ code and you can actually specify which GPU you have, right? So it gives you an option to select different types of GPU, and then it analyzes the code and then just gives you an output similar to this screen right here. It tells you the original code will take about 0.78 seconds, but then if you accelerate the code to offload to GPU, then the same code will actually run on 0.47 seconds, right? So it mainly tells you that you will actually save 21%, and it will actually show you the exact function name, right? The actual loop that has to be offloaded, and it shows you the CPU versus GPU time if you offload a specific section of your code. So this tool, you can mainly it gives you summary of saying that, okay, with by accelerating you got to 3.5x in this example. It gives you all the statistics about which loops are good to offload and then which loops are not a good idea to offload, right? Which mainly telling that if you just let it run on the CPU, you will get better performance than offloading, because offloading does you will lose some time because of memory copy. So this tool actually takes into account how much time it takes for memory copy versus computation, and then whether it's worth it to actually do the offload. And then it shows you the exact code in lines of code, which will actually help you analyze which parts of the code can be offloaded, right? And so I can show you a working demo of this on the dev cloud. So if you go into dev cloud and the oneAPI essentials folder, so there is the module 5 and 6, which is focused on the tool itself. So there's an Intel Offload Advisor notebook, which gives you all the information about how to use the tool, and then what are the command line tools that you have to use to get the to do this analysis, right? And then if you go into assets, there's actually a live report. So this tool will generate this HTML file. If you open this HTML file, it will actually show you what the tool will look like. So in this case, I think we pre-analyzed like a matrix multiplication example, and it generated this output, right? So it's mainly showing you will get about 3.5x performance compared to CPU versus GPU. You can look at different offload regions. It's mainly showing which specific loop you will get a better performance. You can display the call tree and then find out which sections of code is taking what's the elapsed time for each one of these loops and executions. Right. You can also look at the actual command line. The tool that was used is just a simple Python command, just running this one along with your binary, right? So in this case, the binary used was the matrix multiplication output. So you can specify A dot out or whatever your binary is, and then just use this command. This will actually collect all the data and then analyze it for you. And it will generate the HTML report, which you can view and then decide whether to modify your code for acceleration or not. Okay. So same thing for this topic as well. There is I think a 90-minute version of a workshop that was conducted, and you can access those modules if you have more information. Or like I said, if people are interested in any of these tools and need more information, we can obviously come back and then conduct a full workshop, more hands-on workshop for each one of these tools. And the last topic I wanted to cover today is the Intel VTune Profiler. Again, the dev cloud comes with VTune installed. So mainly what it allows you to do is just profile your code using the command line options. And once you profile the code, it will mainly generate a directory with all the data results, and you can copy over that results to your local machine, and then you can analyze it much further using the actual VTune installation on your machine, right? So there is a Linux and Windows version of VTune that you can install. So it mainly shows you the command line, what you have to run to do analysis of your application. So you have your A.out is your application. And in this case, you're just collecting all the GPU hotspots, and the resulting directory is called vtune_data, right? So once you run this, usually this tool will take about 20 minutes to run, and it would have created a directory called vtune_data, and you can use that result file to actually do your analysis, right? So so you can see the command line. So you first compile your command, right? Your actual application, and then you run your application. And after that's done, there is a script that will help you to collect all the information. And usually this, again, I think takes about 20 minutes to do. And these are all the different options. If you want, you can try by default, I'm just collecting the GPU hotspot. But if you want to collect other information like just the memory access, you can just uncomment this one and then run the script again. And all this will do is like it will create a directory called vtune_data, and then it will collect the GPU hotspot data, and then finally we ask it to create a HTML file, right, which will give you the summary. But if you want to do more analysis, you'll have to have the VTune installed locally on your machine, right? So I have a copy of VTune installed locally on my machine here. And if you go to the welcome page, so I have some vtune_data projects that I've copied over to my system from DevCloud. And once you open this, this will actually show you the summary. So this summary is actually generated in the HTML, but all of the detailed analysis can be done using this local installation. So if you look at the actual analysis, it will show you the performance time, what exact command it's running. So if you hover your mouse over it, so it will show you it mainly module create versus command queue synchronization time, right? So it will show you all the different aspects of the code here. It will show you the workgroup size. Mainly it's showing that the global size was 1024, local size was 256. the average time it took, if there was any, what's the SIMD width. It gives you a lot of information about performance, and you can use that to optimize your code. It shows you how many EUs are stalled versus idle, right? And then the peak thread occupancy. So based on that, you can change either the workgroup size or the SIMD width and see if you're getting any different computations. So these are the main 3 tools I wanted to cover. So let me know if you have any questions. So I think, yeah, that's all the presentation I had. I know like the last section, the 3 tools were kind of a short demo sessions, but then if there's interest in any one of these for a more in-depth workshops, we can certainly come back and then do this topic some other time. But if you want to access and learn by yourself, I mean, the GitHub link that I pasted has all the information. There's also videos on the Intel website, so you can just Google any of this and then just Google for CUDA to SYCL migration workshop. You will find a lot of past webinars and workshops that we have that you can definitely view, and then reach out to us if you have any questions. So with that, I think we are open to any questions. Yeah, if not, we can wrap up the session.
Thank you so much, Rakshith. And you guys can always shoot questions after this event as well through email. Any questions that you have will be answered offline as well. And
yeah, let us know like what kind of topics you would like in the future, what will help. I mean, this mostly covered all the basics. If you want more advanced topics for your projects, I mean, we can definitely deliver that.
I'm sure a lot of the students who are ramping up would also be interested in Intel Compiler as well, other than Advisor and rest of the tool set. Even those who are working in the machine learning area or AI area, there are a lot of AI tools as well that we can give in-depth training as well. So it doesn't have to limit only to the tools that Rakshith talked about. So that said, thank you so much, Rakshith. That's a wonderful presentation on your behalf, and Ben as well. And all of the folks from the University of San Diego side who really helped facilitate this and get this to fruition. Really appreciate Mary, Susan, Andy, a lot of other folks as well, Matt. Any other comments before we wrap this up? Andy, Mary, Susan?
Yeah, I just wanted to say thank you for the nice training and the presentation. It's really great to have this introduction, for our students here at SDSC and at UCSD. And yeah, it's a great event. And yeah, I look forward to maybe doing something more advanced in the future. I think there is one additional question in there. If you can comment on that. Interesting question is CUDA allows producing single binaries supporting multiple targets. Is something like that possible with IPCX, Clang++, etc.? So I think,
actually there is one other question there from Nanda.
Yeah, so I think so we can do similar by using so you can access multiple devices using just using device selectors. You can say you create a queue using GPU selector, and you can specify that to only pick, like, let's say Intel GPU, and they can create another queue to pick only NVIDIA GPU, and you can submit different tasks to different GPUs if you have multiple GPUs on the same system. We had the code for, let me see if I can bring that up real quick about.
I think he responded. He remembers now.
Yeah.
This code sample. Thanks, Rakshith.
Yeah. Yeah, please reach out if you have any questions. I mean, we'll be happy to answer and then provide you examples. The GitHub repo that we have has like, I think about hundreds of examples showing different features that will be helpful as well.
And also one quick note I would like to also add outside of this, I want to digress a little bit. So those, who are students and who are interested to really ramp up on oneAPI and become student ambassadors, we do have what's known as a student ambassador program. So there are a lot of benefits associated with it. I think Andy is aware of that as well. So if you guys need a presentation on that, I can arrange that as well. So a lot of benefits for students who are in different years of their graduation, and once they graduate, it really helps a lot when they go on to look for other opportunities in companies like Intel and elsewhere as well.
Thank you so much. We definitely have students who will be interested, so we'll make sure to follow up with you about that.
Absolutely, thanks.
Yeah,
Thanks
and thank
a
you so much for putting this together. This is a really wonderful workshop.